void strategy. So coming to the void strategy, should I continue? So these voids have given way for community spaces to a very deprived community. These voids have given way for various social, cultural, community, and shared amenities like shared appliances, recreational spaces, gardens, etc. Yeah. So again, these voids have given way for various community spaces to a much deprived community. So they gave way for basking balconies, urban recreational spaces, common appliances, and such. We have activated the ground floor and the street level by reserving the bottom 3 stories for commercial and community uses. We like to focus on the second story, which is the community kitchen. The community kitchen uses Scheffler dishes on the rooftop to use a solar-powered cooking fuel. This reduces the demand on an utility like natural gases and reducing our carbon impact. Coming to our material and envelope portfolio, we especially focus on second life materials like agrocrete blocks, which are made from agricultural waste. And also for our insulation, we have selected cork, which has a lower embodied carbon, while at the same time giving great thermal performance. We have iteratively selected our R value, which complies with the Indian Green Building Standards. Mumbai, being a coastal city, has a climatic zone of 0A, which is a tropical, warm and humid climate. So the Indian model of adaptive thermal comfort recommends a cooling set point of 25 degrees Celsius with a relative humidity at 50%. We calculated the load of the entire year, and we found that the latent load was significant in Mumbai. Also, the peak load helped us to create an HVAC system, which is designed for the same. Our HVAC system specifically looks at latent load and sensible load separately. This has proven to be in research as a very effective way to reduce our load. So the latent load and the sensible load both use vacuum pump technology along with membranes to create a cooling effect as well as dehumidifying the air. On the rooftop, we have installed the sensible system, which is a vacuum insulated chamber, which pumps chilled water throughout the building. On each floor plate, and each apartment, we have a dehumidifier, which is part of the latent system, which removes the water vapor from the apartment and releases it into the ambient air with the help of a dew membrane. This entire system has given us an exceptional COP of 7.4, which is 91% better than a conventional 5-star split air conditioning system. We have also achieved 60 to 85% annual energy savings with this system. Using water as a working fluid also reduces the environmental impact associated with CFCs or such, and 43% lower operational carbon emissions across the entire system has given an excellent HVAC system. Now coming to a water strategy, our building utilizes 60,000 liters of water per day. So to target and reduce this water demand, we have employed gray water treatment using gravity systems, using water efficient fixtures, as well as using rainwater harvesting. And this has allowed us to reduce our annual water demand by 80%. Also enabling the gray water treatment on site has reduced the demand on the city sewerage system, and we have avoided 200 tons of carbon dioxide equivalent in the system.
So coming to energy, to reduce the energy demand, firstly, we updated our lighting system to efficient automated lighting, followed by switching HVAC system and plug loads to central level, which further reduces our water consumptions. In total, using these techniques, we are able to reduce our electrical demand by 44%. By using rooftop solar PV and building integrated photovoltaics, we are able to generate 141 megawatt hours of electricity against our consumption of 120 megawatt hours, which makes our building net positive energy. Now here the graph shows the generation and load pattern across the year with grid feed in and feed out for each individual days. Our smart demand management systems takes weather data, occupancy, and renewable production as an input and uses mentioned algorithm to predict the load demand, building load demand. Based on this, and also taking grid load profile into account and market pricing, it gives different recommendations, and using this we can shift our manageable loads for maximizing renewable energy generation and minimizing grid dependency, while also giving us optimum power to cost ratio. In addition, apart from demand shifting, We also leverage a smart energy meter for real-time energy pricing, which enhances the efficiency of the battery uses and also tells us when we need to charge or discharge the battery while decreasing or minimizing the electrical cost. Overall, using these techniques, we are able to reduce our dependency on the grid and by leveraging both PV and the battery power during the peak hours. Now let us understand this by taking a case. So for Indian scenarios, usually the peak loads are during the morning time and the night time. Now these loads can be shifted to solar hours, which also maximizes our solar energy utilization and also takes tariff rate into account. In case of grid disruption, we have divided the load into two parts, essential loads and the critical loads. Essential loads has a backup of 3 days for each dwellings, whereas the critical loads, which includes elevator, pumps, and corridor lights, enjoys a backup of 7 days. We also conducted risk analysis in case of battery failure and PV failure, which has a very less chances of 0.05% per year. Overall, in terms of EUI, we have reduced our EUI to 73% using different active and passive methods. Our source EUI came out to be 20 kBTU per feet square per year, and it further reduces to minus 3.92 kBTU per feet square per year using renewable generation.
As per the cradle to grave life cycle assessment, our retrofit has been able to avoid about 6,800 tons of carbon dioxide emission by mostly concerning the operation carbon. Further, the post-retrofit life cycle emissions are considering the net zero carbon over the life cycle. We have able to sequestrate about 102 tons of CO2 emissions. For further reducing the carbon, we have proposed circularity in terms of resources and materials. Starting with the renewables, we have proposed efficient water management systems and solar power generations for energy as well as cooking. For demolition waste, which have been generated during our retrofit process, it has been used in the building itself. The structural steel and the UPVC panels can be reused after the demolition of the building. We have also used the recycled agricultural waste materials like agrocrete blocks and agri-bio panels, which further reduces our embodied carbon.
Now, now, the entire cost of retrofit comes out to be about $500,000. If we assume an 8% interest rate to account for the net present value, we can see that the capex cannot be achieved relying on savings alone in a realistic timeline. However, this provides us avenues to provide for innovative business models. For example, if we take a monthly rent per household of $35 to $40, we can see that the payback period can be brought down to just 10 years. Additionally, this rent includes the cost of utilities as well as the cost of maintenance, yet lies below 10% of the monthly income to mortgage ratio of our target market. This ensures affordability and feasibility for our occupants. Now, of course, retrofitting is a bit cheaper than new construction, but our active systems pay back for themselves just by their savings. For example, the solar kitchen and community dining can be recovered within 3 years while saving 1,500 tons of CO2 equivalent over its life cycle. Similarly, the HVAC systems pay back within 9 years while saving about 1,200 CO2 equivalent. And while the project breaks even in 10 years, the investment in PV and battery systems can be recovered in 13 years while saving a drastic 6,000 tons CO2 equivalent over the life cycle. But why retrofit? Of course, if we look at our new construction is at least 8% less carbon intensive as compared to retrofitting if we follow the same material selection and system design. But here's the catch. New construction is also 67% more expensive than retrofit. Thus, this suggests that we should go for retrofitting to appeal to our target market much better. Now, SRH buildings perform worse than slums while increasing the cost of utilities. However, our retrofit Samsara not only reduces the cost of utilities, but also enhances the quality of life significantly. We achieve this by shifting our cooking fuel from natural gas to solar generation, enhancing daylight penetration, providing community and open spaces within the building, while also achieving thermal comfort using our efficient HVAC system. Now, not only does our proposal enhances the aesthetics of the SRH building, but also provides avenues for social interaction and community empowerment. In a nutshell, our occupant benefits significantly with an increased floor area, habitable area of 360 square feet. Our entire building's source EUI has been reduced to negative 3.9 kilobtu per square feet per year. Also, our in-house developed innovative membrane-based heat pump system performs significantly much better than the traditional HVAC system. Also, our design performs much better in terms of passive performance, where natural ventilation has been increased from 1 ACH to 4 ACH. Daylight autonomy has been increased by 35%, while thermal load has been reduced by 28%. Also, we achieve all of this while drastically reducing the monthly income to mortgage ratio by 45%. Moreover, our design is that positive energy, net zero carbon, which is traditionally offsetted from on-site generation and solar-powered cooking, and also net zero water, as per the Indian Green Building Council's rule of 75% threshold. Lastly, entire process can be completed within 6 to 12 months, depending on the type of construction and the type of material selected. This also ensures that not even a single occupant or even a single household is displaced during the process, because most of our target occupants actually rely on daily wage and actually work as construction laborers. So not only do we provide a sustainable way of adding the retrofit, but also ensure that we create some jobs which also empowers the community overall. We would like to stress that not only do we retain 100% of the existing structure, but also retain 60% of the existing walls. Lastly, thank you for your time, and please let us have your questions.
All right, thank you so much, IIT Bombay, and we are going to move into our 12-minute Q&A. So I will start with Julie first.
Thank you so much for your presentation. Can everybody hear me? Is that loud enough? Okay. Excellent project, very comprehensive and integrated. I really appreciated your subtraction strategy. You know, we tend to add more instead of thinking about what we have too much of and how we can move it around. So my two questions are related to program and planning, space planning. In your floor plans, you seem to have the same furniture configuration in all the spaces that appear to be one-bedroom units. And I imagine that these units are occupied by families. So how do you see, and you talk about also in your proposal how future tenants will be engaged in selecting their own units and those kinds of things, but the plan, they all look the same. So can you talk about how you envision a family occupying these spaces and how the location of the closets and the windows might impede some of the flexibility in some of those bedrooms?
Thank you for your question. If it's all right, I'll go ahead with this. So just to go quickly ahead, actually, Indian residential market is dominated by something called the carpet area, which is also known as the habitable area. All land, all apartments are sold as per that, right? So there's a strict rule in terms of how much carpet area can be given to what kind of affordability and monthly income, right? Although we have that limitation, but we ensure a free plan concept where although all units are the same area, but since the walls are lighter and they require much less construction time, each household can individually be reconfigured as per a family's needs. So that's how we ensure participatory planning and ensure that families get their house like they want.
So the plans that are in the package are not the reality. It's not going to have a double bed in every one bedroom in the same spot.
If a family needs that, sure, they can have it. And of course, like I said, typically the interior construction would take about 15 days to 30 days, depending, of course, on the quality you're going for. And the materials, the wall materials are much lighter. And as per the company, as per our industry partners that they suggest, walls can be erected within a day itself because they're so light that a single person can lift an entire wall.
And then the one other question I had was you had said earlier that you take the worst performing units and you remove them and then you put them on the top of the building. I would assume that the existing building has an identical floor plate stacked on top of each other, but you don't take a straight, you know, cut out of the building. So how are you thinking about that?
Once again, should I go ahead? Thank you. Right. So of course, there's a lot of units and there's a lot of combinations that we can go for to remove the worst performing units. We relied on ASP, which is a multimodal decision-making framework. And that way we prioritize the parameters as per the community's inputs, right? And after that, we put this framework into a quantitative framework, which is TOPSIS. TOPSIS gives us an ideal negative and an ideal positive solution. And of course, if we remove those straight line of those units that are near to the other building, that would be the best solution. But it would add a lot of significant cost in terms of structural repairs, because removing a lot of units and creating asymmetry would result in long column effect as well as short story effect. So that's why we, how do I say it, optimize between the ideal negative and the ideal positive solution by selecting the best performing iteration.
So can you help me with what you're going with when you're talking about worst performing? Can you describe what you mean by worst performing a little bit more specifically?
Right. So let's say ACH, right? A lot of, especially after COVID, a lot of rules and regulations got revised, and they suggest that each household should have at least an ACH 3 to 4 years, while currently they have it less than 1, right? And that way we have a threshold, like for example, once simulation starts, all households get listed as per their performance. Out of them, either bottom 20% can be removed or the top 10% or 20% can be selected. So that's how we select the worst performing units and go on iteratively as per different parameters. I hope that answers your question.
Yeah, I'll take that for right now.
Okay. I mean, if I can add more, is it okay?
Just a hair more, because I'm gonna give them a little bit.
Okay, all right.
Just a hair. If
All right.
you-
So same thing can be applied to daylight autonomy, where it's 10%, less than 10% right now. And we can select which ones are performing much poorer than, let's give a threshold of 20% or let's 30%. But on an average, we achieve 45% of daylight autonomy for all the households.
No, Ash, yeah.
Right, thank you. I think you guys have done a great job selecting the project to begin with. I think that's where much of the impact you can see, because it's a scalable project. There's so many buildings around you where you can do the same structure. They don't have, only 3 buildings have the 10-story construction, so that restricts you in some way. So you would not be able to follow the same, taking the units out, worst performing. But except for that, I think it's a great project you have selected. I have couple of very simple questions. The first is when you're taking the units out and before the construction is completed, how do you think it's going to disrupt their daily lives? Because they don't have like a way to, go to a different location. So how's that going to impact them?
Right.
That's my first question.
Thank you
Yeah.
for your question. Would any one of you like to take it? Should I go ahead? I am very selfish here. Right. So like I said, a lot of Indian construction relies on hand labor as well as small machinery. Of course, it's an existing building, so heavy machinery will be much harder to get on the top of the building. Right. So we start by constructing the new floors on the top, and iteratively and step by step, we go on making those new buildings. While when they are completed, then we start removing the poor performing units, starting with the bottom 3 floors, because they will be affected much more because of the flyover in terms of acoustics as well as air quality. So that's how we go floor by floor or step by step.
Yeah, thank you. The other question I have is about the solar, like PVs and BIPVs you have. Have you looked into the efficacy of how different they are for BIPV as compared to the rooftop PVs?
Sure. Would you like to?
So for solar PV, which are there in the rooftop, compared to the BIPV, has a higher efficacy, provides a higher generation, whereas the number, due to the constraint in the space, rooftop space, and also due to the constraint in the overhang which we are providing through BIPV, we have limited numbers. Like the rooftop has 120 and the this facade, south facade, has 72 BIPV. So the exact number in terms of quantified number, the rooftop has approximately 19% of efficiency, whereas the generation of BIPV, using BIPV, the overall generation increases by 10 to 12%.
Perfect. Thank you. And like the reason I'm asking this question is because the idea is very scalable. I really appreciate you taking the opportunity to find a project like this, but this might not also translate exactly the same way to other projects. And the third question I have, so I'm also from India, and I know there's a way of living there, right? Like we have individual kitchens, we don't want to share sometimes. And you're suggesting a community kitchen at the same time. How do you think it's going to affect their daily lives? And have you done some interviews with them and like really ask them the question, is it okay? Do you like that? Or how do you select that thing?
So firstly, I'll add on, then I'll start and then they can add on. Apart from community kitchen, we have also given them a solar oven, which is designed by IIT Bombay itself and patented technology by IIT Bombay, which gives a leverage that if they don't want to come to the community kitchen and they want to have their own cooking, they can also do that using solar itself. And I think regarding the interviews,
we conducted the interview where few of them wanted the individual kitchens, but there were few who were working and they did not have time actually to do the household chores like in the kitchen. So they suggested that we would like to have a community kitchen. Even if we talk in terms of opportunities in Mumbai specifically, we have dabawalas. That's a particular profession where you provide food to other people, right? So community kitchens will also empower them in terms of monetary benefits.
Perfect. Thank you.
Got about 3.5 minutes left.
Well, because I interrupted Jason, if you want
Go
to,
for it.
all right. Okay, because I mean, picking up exactly where you just left off with the community kitchen and actually how you say it's scalable, but what I really, really appreciate is how specific it is to this site. I think that is the benefit and the beauty of the retrofit is that what your solution is crafted to not only what this architectural type is, but it is crafted to the community. It is very in tune with the community. You're not just saying, well, I'm going to put market rate back in here because that's going to be beautiful. It's like, no, I'm going to make sure that these people can stay where they are. You're enhancing their quality of life and things of that sort. So where I'm drilling into is a little bit more of the constructability because I'm still a little bit hazy on how you're moving and shifting the loads. I can understand and buy the idea that, you know, the structure was made for 15 stories, so we can add 15 stories on top. But I'm not sure if the story is helping you by saying, I'm going to take the worst performing and then shift them up top. I'm not sure if that's actually accurate. I think removing them to create interesting spaces or community benefits is great. And I think your evaluation of saying, if it's the least performing mechanical systems, I just don't want to replace it there and I'd rather put it up top there. That's cool too. I'm just having a hard time understanding structurally how because you essentially said it right there, that the asymmetry would not work. But then when you look at your diagram, it's kind of asymmetric on how so can you talk a little bit more about that? Even in your model, you can see where you're carving and pulling things out. Can you just
Right. Thank you.
Thank you.
All right. So just to inform all of you, our current structure is actually shear walls. They are 300 thick, and most of them are at least 2 to 3 meters long. So symmetry, as we did the structural analysis, it comes out to be the X direction and the Y direction cross section area of these shear walls has to be equal first. Then, of course, if we remove a lot of units, it will create structural imbalance. That's how the first criteria that we select to remove the iterations is that our height should not go beyond 2 to 3 floors. As soon as we go beyond that, it will start inducing a lot of cost to repair the structure and to make it structurally stable. This also reduces the amount of structural steel required, because let's say if we removed three dwelling units from a single line, we'll need to provide bracings, right? So that at least the earthquake loads are taken care of, right? I hope that answers your question. And just to go about the scalability part of it, we agree that this retrofit is very much specific to this one or these 3 buildings. But this process can be applied to new buildings where this could be a Pareto optimal approach, where maybe not remove one worst performing unit, remove one of them to improve the performance of the remaining units. So for that, we are actually working on a cellular automata approach. We could not use it in this particular project because, of course, retrofitting an existing building, but we hope to develop it a really strong and well-bounded approach, which can also go floor by floor and develop new construction.
All right, that is going to wrap up our Q&A. We'll get to you next time, Jason. So thank you so much to IIT Bombay. Can we give a round of applause? And next up, we're going to have the University of Cincinnati.
I went first, I go last.
All right. Is the University of Cincinnati here? All right, perfect. All right. University of Cincinnati, whenever you guys are ready, feel free to start and I'll start the timer.
Hello, thank you for joining us. We are the University of Cincinnati. Our project is Eden Punt, located in Amersfoort, Netherlands. It is a multifamily older adult complex. I'm Sophia. This is Emily, Julia, Dylan, Jessica, Bob, and Weston with us today. Our city narrative is that the Amersfoort area has proposed 4 net zero new construction projects to boost the city's involvement in sustainable construction and relieve stress from the city's grid. Of the 4 projects, ours will serve as an older adult multifamily community. Our driving forces were efficiency, walkability, and community involvement. We explore the use of solar panels and sand battery storage to achieve our net zero goal. And our mission statement is to provide a place where older adults can live sustainably in physical and mental wellness while enjoying a welcoming and inclusive community atmosphere. A little bit about the climate in Amersfoort, Netherlands is that it's maritime. There's a lot of rain and it's heating dominated. We have a little bit about our daylighting and the precipitation throughout the year, as well as the winter and summer solstice, the winter being down at the bottom, and then obviously higher in the summer. This is the proposed local microgrid. Ours is the triangle site up at the top with our sand battery storage. Right now, the Netherlands is overproducing and throwing away green energy in the summertime, and they don't have proper means of storage. So our site wanted to provide a solution for the city as well as our site to achieve net zero. So this is how we've decided to do that.
For our building program, we have a total of 12 floors at approximately 98,000 square feet. And it's split up into residential and commercial. So for our residential, we have apartments, hotel, and amenities such as a gym and pool. And for our commercial, we have a library, coffee shop, and bike shop. For our site forces, our site is in the green. And above us, we have a commons and plaza. And to the left of us, we have an apartment complex that's about 15 stories. So that influenced the height and shape of our building. And for our site strategy, we wanted to promote health for our residents and the environment. And to do that, we have green spaces for our residents. And we also have a community garden program. We have an amphitheater to the south of our site. We have an outdoor workout space. And we also are approximately close to a train station and also implementing solar panels. To go into more depth of our floor plans, early in the design stages, we came across the concept of the 8 dimensions of wellness, and we wanted to choose commercial spaces that fit into this concept. So on the west wing of the building, we have included a bike shop that will be popular because bikes are one of the main modes of transportation in the Netherlands. We also included a library and a coffee shop, which fits within the criteria of mental wellness. These 2 spaces will be open to the public. On the other wing, we have included a pool and a gym, which fit in the criteria of physical wellness. And on the second floor, we have included a second story to the library and coffee shop, which will have elevators to improve accessibility. We also have a physical therapy area, which tailors more to our older adult residents. There are some private offices in that area as well, and there are some offices located towards the center of the building for administrative purposes. On our third floor, we've included hotel spaces, which can be used by visitors of the residents or by local university students. And on our 4th through 11th stories is where we have our residential units. These units range from studio to 3-bedroom apartments. We've also made sure to keep the hallways a little bit wider to improve accessibility for wheelchairs or things of that nature.
One of the most exciting challenges with the multifamily portion of this competition was obtaining net zero in and of itself. The sheer size of the building really makes that evident. So the first three things that we wanted to break down and focus on were our daylight analysis, maximizing incident solar light and radiation for our solar panels, and improving solar comfort, our envelope efficiency, which with our optimization of our envelope and balconies, among other things, really presents a unique challenge, and our building loads as well. So starting with our daylight analysis, we oriented our building so that a lot of the units will face the south end of the site. However, that presents a really big challenge, as Sophia introduced with our maritime climate. Light is very difficult to get into the north end of the site as well. So we have balconies for each unit on the 4th through 11th floors. And so we decided on the south end, we'd push those balconies inward. And on the north end of the site, we would pull them out in order to maximize the amount of light that just can get into the units in general. However, that in and of itself presents a unique challenge as well, especially so depicted here. We have the extended balconies. And so that was very difficult to maintain that air barrier, vapor barrier, and water barrier. So we decided to, and also seen in the bottom left are our baseline U and R values, which were pretty abysmal. We'll go through our life cycle analysis later on, but it was very difficult to optimize those. So we decided to increase our insulation. We did a double insulated layer, and we improved our glazing, especially. The storefront already is a big loss, so we decided to increase the panes and the mullions for that. And depicted there in the wall section, we have highlighted the unique water, air, and vapor barriers.
So another challenge that we had with the size of our building was mainly the building loads. We are in a heating dominated climate, which essentially means that most of our energy consumption is going to come from space heating. When we looked at the hourly data of temperature for the whole year, there are only about 153 hours that would require cooling. So our HVAC system mainly focuses on providing optimal and adequate space heating for the building, but obviously to be code compliant, we are still providing cooling for the building. And as you can see to the graph to the right, our space heating is the most amount of energy consumption and use. And when we went from our baseline to our new loads, one of our big goals was to significantly reduce that space heating. And then with other energy efficiency measures, we were able to go ahead and reduce that, even our lighting as well. So another challenge that we have is, since we have such a large building, we needed to figure out how are we going to power this whole building and how are we going to eventually achieve net zero. So starting with our baseline EUI of around 53 kBTU per square foot per year, we were able to bring it down to around 37, just with several different energy efficiency measures, whether it's optimizing our envelope system or improving our HVAC system. And then one method for us to bring down to zero is to go ahead and use several different renewable energy methods, one of them being photovoltaic panels. So we calculated that we need about 60,000 square feet of PV on our site in order to bring us down to net zero alone. We found that our site is able to account for 45,000 square feet. And so the way we are able to get the rest of the energy still needed, about 300,000 kilowatt hours per year, is going to be through our microgrid with our sand battery storage. So as you can see here, when we are using just the PV panels, we would have an excess of production over the summer and then an excess of consumption over the winter. As you can see in the graph to the right, in total, there is more consumption than production with just the PVs alone. So we'll explain more about how our sand battery will make up for this fact.
So we're using a sand battery to store the energy. And as Jessica said, we have a lower amount of production in the winter. So we're using sand battery because it can store energy for long periods of time. So we'll take all the excess energy from our grid and the other 3 sites in our microgrid and store it in the sand battery and then release it to the building whenever we need it in the winter. And then for structural, we have a concrete foundation with steel beams. And then we're using wood framing for any non-load bearing walls to reduce the carbon footprint.
Continuing to move forward and assess some of the engineering aspects of our building. The mechanical HVAC system was something really important to our building, especially concerning the concern of building loads. So we found a system which is a variable refrigerant flow system that actually is hybridized with a water loop. So this water loop will actually condition the refrigerant in the building. And then that refrigerant will then be pushed out to each of the spaces air handling units to properly condition the spaces. The interesting thing about this system too is that VRF systems can be used in both heating and cooling times. Obviously in our building, we're primarily going to be heating, but if a space does need to be cooled, the system has the capability of doing that as well. Our water loop will be primarily conditioned geothermally. However, to start to implement the usage of our sand battery, we found that we can have a backup means of conditioning that water with excess heat from the sand battery. And then obviously then that will be pushed into the water. The water will condition the refrigerant again, and then condition the spaces properly. Lastly, we needed to bring in outdoor air still into the building. So what we've designed is essentially a passive dedicated outdoor air system that will, so it's essentially that big spine structure that runs through the model. And each of those branches that break off of that spine are duct paths that will diffuse air into each of the spaces. Considering a life cycle assessment of our building, we had to make a couple material choice changes. We were primarily using a lot of steel in early iterations of our building, which is why we have such a large score for our life cycle assessment initially, but by sourcing locally, primarily in the Netherlands and in neighboring areas if need be, as well as making a couple material changes, we were able to significantly increase our LCA score. And lastly, we did do a building estimate of our entire project, finding that the material costs would come out to roughly 25.5 million USD, with labor equating to about 20 to 40% of that cost. The total cost of our building would be about 36.5 million USD or 33.8 million euro in the Netherlands. And we appreciate your time and we're happy to take any questions.
All right. Thank you guys. And we'll start the 12-minute Q&A. I'll start with Jason.
Nice job, guys. It's a thoughtful design and presentation. Thought you did a really nice job. I'm most curious about the selection of the sand battery. I understand the problem that you're trying to address. It seems like there's excess renewable energy production, and it's kind of a community-wide answer. I'm curious about like the round trip efficiency, because with chemical storage, I think that, you don't have the same losses that are, that you can have with a system like this that relies on storing thermal energy and then producing electricity with a turbine, which is how I understand that system works. So I'm curious if you all looked at the efficiency of, how much, what the losses are when the energy is stored, and what your thoughts are, how you came to the decision on the sand battery.
Yeah, I can talk a little bit more about that. So part of it was we ended up finding the sand battery system, but we found a couple other systems like gravity battery systems as well. We found the sand battery ended up being the most efficient compared to those other systems. It's usually on average like 60% efficiency if you're not also reusing like the heat that could be wasted, because there is going to be heat radiated off that sand battery. So we've actually implemented that as well to help with our building. We've also, because we want to emphasize like the net zero and the ability of this building to be sustainable, we've incorporated kind of how this sand battery has been able to heat our building as well as provide electricity for our building by actually adding in features like we have like little heat vents, so you can actually see that heat like radiating off the building, and you can actually see that in our courtyard in the center. So since we are also using like that heat that would have just gone to waste, we're actually able to like bump up our efficiency between like 80–90% with that.
Cool.
So a question about the building itself is, I heard you talk about the challenges of the orientation and the south facing glass and the challenge of the northern facing. Can you talk to us more on how you oriented the master building and how you got to this particular shape, how it fits on the block and things of that sort?
Yes, so that was a giant consideration. Oh. My bad.
You can put it back to full screen on the computer over there.
So we decided to.
The bottom right.
Right there.
So the difficulty with that was our site really forced us to push the building to the center, located in that roundabout there. And so with the solar instant portion of it, with it having to be in that top corner, we really wanted to do this stair step design as well, which allowed us to put more solar panels on the roof as well. But the other thing was that a lot of the surrounding buildings were taller than ours. So we really wanted to, while we stepped our building in and of itself, when you stand in that roundabout, you see a geometry and a hierarchy of stepping. So it was more an architectural principle that we did that, not very much a engineering principle.
Do you think there are opportunities of reshaping because it sounds like you're saying that you're forced into the corner? Do you think because you are considering the whole site, I think as a group project, is there another orientation or is there an adjustment that you could make to the building, or is this like the ideal placement that you?
We felt that this was the ideal placement for the building. The other thing too is there is a railroad to the southeast end, or just to the south end of the site. So we wanted to avoid a lot of residual noise that would come from that. So that's why we also have the parking garage there as well. And with that too, we have a longer west or northwest leg also pushes both the residents of Eden Punt and the public down towards that train as well, or that train station, so that we're also promoting a more healthy travel to and from the site.
No, actually,
Oh, I'm sorry.
I have a lot of questions, but I'll stick to a couple of them. And by the way, great job, team. It's a great project and very well designed. And I think many of the questions Reggie's asking is about the design because it's a good design. Can we talk about the baseline? Like, how did you create the baseline? Because you're also showing improvements on the south-facing nature of the site as an improvement over the baseline. So I'm just wondering, what was the baseline for you guys?
Want me to talk about it? So we used Jessica and I used a program called eQuest, which is it's a HVAC software that like allows you to make changes to your envelope, and find certain building load elements, just based on changing things like the HVAC system, and obviously then your building cavity as well. So our baseline, eQuest has a default setting with like really low R values, as well as just a not very high quality wall section. So that's what we used as our baseline, was the eQuest default essentially. And then we made changes to that to improve it.
Perfect. And did you use the same design as the baseline, or was it different standard design that you used and compared against?
What do you mean by that?
So
Don't
like,
mind
if you
rephrasing.
look at the shape of your building,
Sure.
like was the baseline the same design?
Yes, it was.
Okay,
Sorry.
yeah.
Yes.
And I just have one more question. When I look at the U values for your glazing and window, they were very different. Like one was 0.5 and one was 0.1.
Yes.
Could you talk about what do you consider glazing and what's considered a window, and why were they so different?
Sure. So one of the settings in eQuest, you can alter, like how many panes a window, right? So you can use like the two double pane, triple pane. So in making changes like that to our building with our window wall cavities, as well as our windows, obviously in our wall section has a U value as well. Those things are all updated as you make changes in the program. That makes
Perfect.
sense.
Thank you.
Yeah, totally.
You said you had a lot. You want to ask another?
I have a whole list. I can go on.
You can ask one. Yours are burning.
No,
Go
no, no,
ahead.
We'll go to-
I'll be fine.
We'll go to Julie and then we can come back to you. No.
Okay. Well, I was just curious why the Netherlands? There are obvious cultural, climate, code, building system availability and maintainability and language challenges that you added to your plate through the selection of this location.
So this project was also our capstone design.
Could you speak into the microphone?
Yeah, sorry. This was also our capstone design project, and our professor Anton, he kind of acted as our client, and he just wanted for it to be a more challenging problem for us. So he designated ours as the Amersfoort area. We also worked closely with, he has family in the Netherlands, so we had local resources that we could like talk to and ask about cultural things and whether people would be interested in a bike shop and like what they kind of do day to day and if they take the train. So we kind of had like a local input there as well, which is another reason that I think he wanted us to use this site.
Oh, those professors.
Those professors, clients.
Oh,
We have 4 minutes left, Milash.
4 minutes. That's
Okay, then I'm gonna ask.
Okay.
You also said that your program type was senior living, and I noticed quite a few 3-bedroom units in the building. So can you talk about the thought process behind that too?
Yeah, so we wanted to, a cultural theme in the Netherlands is that sometimes they will have a caretaker. And then they'll also have visiting family as well, because there's a very high emphasis on comfortable living and like accommodations for older adults in the Netherlands. So we decided, we only included 3 3-bedroom units, so it did not take up a lot of, like we have 56 units and only 3 of them were the 3 bedrooms. So we wanted to include them as just kind of an extra option, but not the main bedroom type. So.
Thank you. Okay, I see my time.
Perfect. Thank you. I appreciate it. So when I saw the concept you have this around the sand batteries, I also did some of my own research looking into commercial implementations. And it seems like where you have the site, you also have multiple more implementations of a sand battery. What's the size of this battery?
It's big.
It's big, right? Like how big is it? Do you
It's
have any idea?
It's about half the site. The interesting thing though about it is that because we're able to bury it in our site,
Yeah.
it'll help condition that sand and keep it warmer for longer.
Mhm.
But yeah, based on like, plus our needs of bringing, sorry, I'm talking into the mic. Plus because we are essentially looking to give some of that energy back when our building doesn't need it.
Mhm.
It's important that we have something that is capable of storing as much heat as possible.
Mhm.
But yes, it is very large.
Perfect. Thank you. I just wanted to make sure people understand it's a large battery.
Yes.
Because like if it's a chemical battery, it's much smaller, but
Yeah.
sand batteries are massive. And one of the question I have, do I have more time? for this?
Yeah, 2 minutes.
So if you look at the daylighting analysis you have done, if I look at the pool area, it's bright. It's over 6,000 lux or something like that. How have you addressed reducing the glare or other issues through the envelope or design changes in those areas?
I mean, we not only are there like operable windows and abilities for shading for the residential areas, but that's also going to be included in the commercial areas. So there's like options for like adding like shaders, operable shaders in that area to, reduce any sort of glaring stuff. The pool itself, the reason why it's so bright is because all of that is just glazing all around it.
So I'm gonna tack onto that just a hair because you're talking about the glazing.
Mhm.
How did you come up with your facade materiality and your fenestrations and things of that sort?
We actually decided on brick for the majority of it because the surrounding buildings are all brick and we didn't want to stand out. It is a historic town, so of the surrounding neighbors are entirely made of brick. So we wanted to use that as our main source and then increase our architectural elements through like our breezeway is glass as well and glazing, and then our pool just to make it a little bit different.
It wasn't traditional masonry veneer, right? You had like it was a thin masonry veneer, ephes it's carved into the ephes, is that?
So it's, yeah, it's a, masonry veneer engineered system, our envelope system. Because we didn't want to have like that significant carbon footprint of just using like actual masonry bricks, but we wanted to match the style of the surrounding buildings, but not have to use like that.
So is it part of the ephes finish or is it adhered to the ephes? How is it?
It's adhered.
It's
onto it,
adhered to the
yes.
ephes.
All right, that's going to wrap up our 12-minute Q&A. So can we give a round of applause for University of Cincinnati?
Oh, very nice to meet you.
Guys, thank you for the question.
Very nice to meet you.
Good job, guys. All right, next up in here, we're going to have the University of Missouri. We do have a few minutes in between.
Absolutely not.
I think we need space to move back, so.
Yeah, we'll give the speaker space.
No, it's like.
Yeah, right.
To walk back. So just like stand right there.
With geothermal heating, you have balance in the roof, if you make cooling, but you actually cool the ground over time, but we maybe find issue here.
Right. Yes. All right.
If you want to move back closer, if you need.
Oh, really?
We're just gonna wait a minute until it's 10:10 because I don't want to get off the schedule, so.
Oh, yeah. For you guys, I'll have a 2-minute warning. I'll kind of hold it up so you guys can see it.
Thank you.
All right, we are going to go ahead and get started with the University of Missouri. So whenever you guys are ready, I will start the timer.
Hello, everyone, and welcome to Lighthouse, a mixed-use multifamily housing complex in Columbia, Missouri. We represent a large interdisciplinary team of undergraduate students from the University of Missouri, Columbia, and Missouri University of Science and Technology. We also received help from industry partners. The building site is a vacant brownfield in Columbia, Missouri, just north of downtown in a thriving arts district. It is envisioned as an affordable living option for international students, early care educators, and their families. Lighthouse's design emphasizes social and physical sustainability through active engagement with the neighborhood, proximity to critical resources, and promotion of a healthy lifestyle. The building supports occupants as they create, make, and balance their lives with emphasis on environmental, social, and economic conditions. Overall wellness considerations are reinforced with a learning center, shared spaces for cultural exchange, and an eco gym that demonstrates the effort required to power light. Our research found that international students and early care educators are experiencing resource deserts in Columbia. As an international student myself, I know the difficulties of transitioning into a new lifestyle. In the past 2 years, I have struggled with the access to resources, primarily due to the lack of transportation, awareness, or knowledge of what is available around me. International students are also not eligible for most scholarships and completely ineligible for in-state tuition. These situations are why we designed Lighthouse, to help those coming into Columbia from afar and provide for those already here. The site for this project used to be where the production of electric lighting first began and housed a coal and gas plant from 1875 to 1932. Over the years, the site was polluted by coal tar, which leaked into the ground and buildings. Thankfully, in 1994, the Missouri Department of Natural Resources began soil remediation, where 31,600 tons of soil was cleaned up and is now safe for use. The name of the project, Lighthouse, is to memorialize the history of this site, the site that turned on the first lights in Columbia. It is a place that guides its occupants towards sustainable, affordable housing and living. A 15-minute city is a community that allows people to access resources within 15 minutes by foot or bike. Lighthouse is centrally located between 3 dominant collegiate institutions and provides sufficient access to grocery stores and markets within a walking distance, as well as a bus station for public transportation right across the street. The project site is in the North Village Art District in downtown Columbia and is approximately 2.1 acres. The main direction of prevailing winds is from the south and northwest of the site. Columbia, Missouri falls under the 4A climate zone, but we also designed for 3A zoning in preparation for future climate changes. Since Columbia is centrally located, we experience both low and high temperature extremes. This is critical to understand as we address these extremes in both hot and cold weather conditions. Using the Climate Positive app, we were able to calculate the impact of our landscape design and balance the different impacts through a series of carbon sink strategies. There are 2 on-site gray water retention ponds that will serve as wetlands, and access space on site will be covered in no-mow lawn. This will sequester 217 tons more carbon than it emits in its estimated lifespan. Therefore, the site is expected to reach climate positive within 5 years of its construction.
The process of designing our form began with 2 volumes, a large box representing the residential uses and then the smaller one representing the commercial. We then manipulate these volumes in order for the buildings to respond properly to our site while also having an efficient building program. The residential volume mimics the setbacks of the surrounding neighborhoods. It increases privacy, reduces proximity to noise and to the street, and it also maximizes the potential for light permeation and cross ventilation. The commercial volume accentuates the main entrance of the building, opens up space for our southern-facing agrivoltaic gardens, and it's also moving the market closer to the street for easy pedestrian access. The building is about 179,000 square feet in total, and it's divided into 7 floors of residential spaces and 2 floors of commercial spaces. These drawings show the integration of those 2 spaces. The residential units in orange are arranged around 2 atriums that utilize the stack effect to ventilate all of the circulation space. And there's operable skylights on the tops of these atriums, which allow for these spaces to be semi-conditioned. We also stack the residential units for efficiency of the MEP systems and constructability. The commercial section is multi-purpose with 3 key spaces being the cultural market, the eco gym, and the resilient core. We also include space for professional help and learning center, demonstration kitchen, office spaces for various building employees, and rentable space for community events and gatherings. The cultural market provides a combination of locally sourced food and crops grown within the agrivoltaic garden, and it is a low carbon resource for occupants with limited access to transportation. The Eco Gym equipment utilizes microinverters to convert energy expended during a workout in order to power the lights within the gym, and the maximum output potential for these systems is about 3,000 kilowatts an hour, or watts an hour, excuse me. And lastly, we're including a 6-story resilient core that serves as a safe space for residents during periods of severe weather, such as tornadoes, which are very common in Missouri. And during all other times, these spaces are available for laundry, restroom use, and other small study spaces or gathering spaces. So there are a total of 108 residential units of 5 different types, and 6 of our studio units are fully ADA accessible. These units are designed to meet the needs of our occupants with various backgrounds and to ensure their comfort and wellness, while also reducing environmental impact. We have windows on the opposite exterior walls of each unit, which maximize the cross ventilation. And based on our cultural research, each bedroom has its own private bathroom. The building structural system contains steel columns and beams with bar joist. W sections were used for all the columns and 90% of the beams on the interior, and the spans were kept to a minimum in order to maintain a shallow plenum space for HVAC and electrical. We worked with Dogwood Solar, a local consultant, to select panels, converters, and on-site battery storage for both rooftop and agrivoltaic systems. Dogwood Solar is currently working on an agrivoltaic system here in Columbia, which helped inform our design. So our agrivoltaic array contains about 200 panels, while our rooftop has 1,100. And each of these systems provides sufficient energy for net zero rating, while also leaving enough space left over to maintain ISEP maintenance aisle requirements and some space for HVAC systems on the roof. For Lighthouse's apartment units, we are using a Train hybrid variable refrigerant flow system and dedicated outdoor air systems with an ERV. There are 8 pairs of HVRF and DOAS systems, 7 pairs of which supply 14 units, while 1 pair only supplies 6. The HVRF system connects to the units via vertical chases. The cultural market is a semi-conditioned space with overhead doors and operable curtain walls that allow for lots of natural ventilation during temperate conditions. There are also large fans which provide extra help with moving the air through these spaces to provide for sufficient humidity control within our climate zones. And during colder days, we would close these doors and windows and use heaters in order to keep the people inside comfortable. So for commercial lighting, our partners at Missouri S&T use the interior retail management software to create timed lighting schedules. These schedules turn off the lights or turn on the lights during business hours, or turn them off whenever nobody is around or when there's sufficient daylighting available to light the space. And these schedules will reduce plug loads and phantom energy use within the building. Each apartment unit has a hybrid branch controller, which exchanges heat between refrigerant from the rooftop system and the water within the apartment pipes. These pipes connect to interior condensing units, which condition each room. By using an HVRF, we can reduce refrigerant by 30% compared to a traditional VRF system. And our partners at S&T also use additional lighting software to create a lighting plan for the apartment units, which calculated the foot candle levels for each room and then the proper lighting solutions.
Our envelope wall details of the building target thermal, air, bulk moisture, and moisture vapor barriers. We've minimized thermal bridging by reducing materials that are conductive from the exterior to the interior. All structural components are confined to the interior conditioned space, and careful flashing and sealing has been implemented around penetration such as doors and windows. Moving from the interior to the exterior of the wall, we have 5/8 inch fire-rated gypsum board, light gauge metal studs, and OSB sheathing. A self-healing fluid-applied membrane is applied to that sheathing, which acts as our air, moisture, and vapor barrier. And then toward the exterior, our thermal control layer is a formaldehyde-free, rigid mineral wool insulation. Next, we have metal furring, which creates a thermal air gap, and the metal panels or composite metal cladding. Throughout this detailing process, we gave careful consideration to keeping our control layers continuous through the foundation, through the walls, around doors and windows, and through the roof. To ensure the control layers are efficient, we ran tests using B-Moist based on the wall and roof materials to determine the dew point. We understood that it was important to prevent mold growth or structural deterioration, and we found that we will not reach the dew point inside the current thermal barrier with the current insulation. All of our materials for the envelope are regionally sourced, sustainably manufactured, and furthermore, each material is designed to streamline installation so that installation during construction is efficient. We use Conyers glass vent curtain wall system to provide operable windows for successful cross ventilation. The system includes an engineered polymer thermal separator that accommodates up to triple insulated glass for energy efficiency. We also use metal frame windows that are double glazed with low E coating and argon gas from Quaker, a local window and door manufacturer. To model the efficiency of the building, we use the Ladybug and Honeybee plugins to Grasshopper, which uses our construction materials, quantities, window apertures, shading, and local climate data to calculate the EY of our building. After several iterations, we were able to achieve a score of 32 before adding PV, and our project reaching that low EUI figure allows us to devote less money to PV to reach net zero. So anyway, yeah. We calculated our HERS score by unit layout and room rate by using the black box method, in which we modeled each apartment unit separately and customized the exterior walls to mimic their adiabatic nature. And because our HVAC system is not predefined within REM rate, we customized a ground source heat pump to match our system's tonnage, COP, EER, and capacity. Our units obtained an average HERS score of 38 before PV and 0 with PV. We've designed for future unforeseen extreme weather conditions to ensure resident safety and security. Lighthouse can be considered a microgrid that acts as a single controllable entity and connect to the larger Columbia power grid or stay in island mode. We're implementing strategies to avoid peak usage by preheating water, installing meters, providing a battery backup facility on site that is 20 feet away from the building for safety. To properly accomplish a healthy building lifestyle, dividing our understanding of embodied and operational carbon is crucial. We estimated a 60-year lifespan for all scenarios to adhere to LEED standards. To minimize embodied carbon, Lighthouse is composed of materials that are regionally abundant, sustainably transported, and efficiently manufactured and installed. We refined material selection, maintained a 500-mile radius for most items, and any items that were not within that range, we confirmed with company representatives that they were sustainably manufactured and will only be transported to our site with fuel efficiency. And here you can see a source of several of our primary materials. We used one-click LCA to accurately calculate Lighthouse's cradle to grave GWP, which is approximately 250 kilograms of CO2 per meter squared. Many products are composed of bio-based materials, creating low embodied and operational carbon. Due to the required quantity, our steel is our largest carbon contributor, and that's just as a product, as an embodied element, as you can see from that bar graph there. However, based on our product sourcing, we might be able to reduce that. We are working with a local scrapyard to obtain the proper grade of steel for the structure that we need, and then we're working with a local fabricator to create those members. Now, the local fabricator that we have in mind is using an electric arc furnace, which can save up to 90% of the dust typically lost in steel manufacturing, as well as reduce the carbon emissions by up to 88%. We worked with McClure Engineering to confirm the efficiency during construction.
In our atrium's lobby and a few exterior walls are Semper green walls. These green walls appeal to biophilia, improve indoor air quality, aid in acoustic control, and contribute to carbon sequestering. We also aim to promote healthy behaviors, such as using the idea of an irresistible stare, which was modeled by the Bullitt Center in Seattle. It was important to address fire suppression and smoke control in the central atriums, and we have included a smoke control curtain at the perimeter of atriums on each floor. We have also placed a fan unit on the roof of each atrium for mechanically assisted air movement. A standard wet pipe fire sprinkler system with temperature control heads is present for suppression. There are also hold open doors on each floor of the adjoining residential and commercial passages. Occupants will use a building automation system to interact with the building, and it allows users to understand the building and its consumption. Some features include notifying users of optimal times to open windows for air quality through the weather station and carbon dioxide sensors, as well as lighting and temperature control and a community forum for residents to interact with one another. We thoughtfully selected materials, FF&E, that aligned with the goals of affordability, health, well-being, and aesthetics. We chose formaldehyde-free and low to no VOC paint, and the interior flooring is 100% recycled LVT and has 52 recycled content carpet. Based on research, we have identified apartment buildings located near our site range from 4 to 13 minutes, but they are relatively expensive. Due to the cost of living, international students tend to live off campus, and they look for apartments that provide shuttle systems to and from campus, but they operate on limited times, so their time on campus is limited. Using RS means programming, we obtained a base price, and then we added equipment to get an initial cost of $65 million. There are several rebates, taxes, and grants available to cut down the cost. We get a rebate for all Energy Star appliances, efficient insulation, heat pumps, and a window within every unit. In addition, the low income tax credit is 9% of the total cost every year for 10 years, up to 30% of the building. This brought our cost down to $48 million. Using the LEED 60-year benchmark, we did a 60-year calculation of Lighthouse, and from this, we were able to keep each bed at $650 and pay off the loan in 29 years while also taking into account interest. Then from year 30 to 60, you will gain profit, which will make up for the initial cost. Our approach facilitates community engagement with the presence of the Eco Gym and Learning Center. It provides resources for professional development through the city of refuge, and there's proximity to public transportation, and at the north end of the building is an electric rideshare station. The presence of the food market allows occupants to be independent in daily activities and obtain needed resources. Throughout this process, we have engaged with incredible industry partners, and thank you for listening.
All right, we will get into the 12-minute Q&A. I'll start with Julie this time.
Thank you for this. We've got a lot of exciting building technology. The project, and I'm wondering if you could speak a little bit more about how they're all integrated together as opposed to a solution here and a solution there and a solution here. And then I'd also like to commend you with the spirit of experimentation that you're taking with the green wall system and exploring the different types of plants and how the plants can help with your humidification and dehumidification strategy.
Right. So you're right. There are a few different things that we implemented. And I think that the main thing that ties all of those in together is that we're trying to push a narrative with our project of sustainability. And we believe that to be a mindset as well, which is why we find aspects such as the Eco Gym to work well. For instance, it generates 3,000 watts of power, assuming everybody is using the equipment. And we thought of ways to incentivize that by maybe operating spin classes within the gym since we have commercial capabilities. But the point of it is that the user experience is influenced by the sustainability that we're bringing, and we think that that creates a positive embodiment of the building. So while we're designing sustainability from a system standpoint, we also think that a cohesive, holistic idea of sustainability within our actual architectural programming pushes our idea further.
Thank you. Great job, guys. Very well done. And really well done in terms of highlighting the problems international students face on a daily basis, how they're different from the problems faced by locals or people who have been around with families here. So I really commend you on that. If we can talk a little bit more about how your solution is actually catering to that problem that you were highlighting on a fundamental level.
Yes. The location of the site is one thing because it's closer to three dominant campuses. And as an international student, if I could walk to my campus and not worry about a shuttle system and not worry about timing, that's one thing that's very big for me. I can go to campus and I can enjoy the events, but not worry about missing a bus and reduce my time and not have friends sometimes. But, but yeah, location of site, access to resources. There are nearby markets and grocery stores that I can access, international markets particularly. Yes, that's mainly the reasons. The main things that we need is one, food, access to campus, school, and yeah.
Perfect. Thank you.
Thank you.
Well, I guess I'm on question C of my list of questions here. First and foremost, I think your presentation has really brought this project to light. The comprehensiveness of your solutions. I mean, your drawings were just a chef's kiss. It was really beautifully done, and actually, I think technically savvy that I could really see this done. And so it's like the question, so when is this actually getting built in my head? And so I'm having, this is trouble. This is funny. I'm having a hard time coming up with really solid and questions that will, let's push the edge. So I'm gonna kind of throw and want you to highlight something that I'm trying to understand is, and I think actually, Julie, you started to ping on this. There are a lot of solutions that you have here. And I think there are a lot of practical solutions, but is there something that you can call it extremely innovative? I think I can see some, but I really want you to highlight that and bring that out for me. What do you, those 2 or 3 things that are just extremely innovative, that are just challenging and different? I think I heard a couple, but I want you to pull that out for me a little bit more, please.
Yeah, sure. So I think that whenever we were product sourcing, we didn't want to settle for what seemed immediately like the most sustainable option. And I went on a little bit about that with the steel process. And if you're curious about that, identify. So essentially what we did with steel was whenever I was trying to find a low carbon option for steel framing, which is what we ultimately decided was the best product for our structure. I came across Nucor Steel, and they're a big corporation, and they have mills and they own recycled steel facilities everywhere because they maintain at least a 74% level of recycled steel content within their structure. Now, the problem was I found that they had a a scrapyard in Colombia. However, they outsourced it to a mill that was really far away to actually create the members. So then I thought, we can do better than that. Let's find a fabricator within Colombia. And then I got to researching and found out about the electric arc furnace. And then I found out how much carbon we could actually save by doing it that way. So this number here, the embodied carbon looks really high. I left it that way so that it stayed consistent through what like the one-click model achieved and what I input. That being said, that could get reduced a lot further. So I felt that that was an innovative option. And I think we have different opinions on what the most innovative things are. But
Somebody else, anybody else?
For me, is the agrivoltaic gardens. I love that idea. I really wanted to implement a community where people can grow their own goods and be able to manage it, but also have nearby, because the bus station is a farmer's market also. So during that time, they could also use that space. And the university also has a group that does this. They use gardens, and it'd be a space that everyone can utilize. So yeah, that's one of my agrivoltaics. Yep.
So, well, I'd like to hear more about that. Seems very challenging just in terms of the wiring and like make sure they don't get dug up and having like meeting fire code for photovoltaics, which is challenging. So I'd like to hear a little bit more about that. And then the other question I had was I didn't really understand the stack ventilation concept and how that tied into the atrium. And I was just hoping someone could elaborate on that. So like I said, two questions there.
So in the atriums, the tops of the skylights have operable curtain walls on them. So then with like the stack effect, the hot air at the bottom is pushed up to the top through those windows. And we also have fans up there to help that in case there's like a higher amount of humidity in the air. And there's also operable curtain walls in the egress stairs too, to kind of help push air through and up to the like tops of the atriums.
So it's you're ventilating the common area, the atrium.
Yeah, the circulation
that's
space
what's
between
being
all the
addressed,
units is what's
circulation,
ventilated.
the
Yeah.
circulation space. Okay. Okay. Yeah, that makes sense. So the thermal boundary is the thermal boundary is not between the units and the atrium. It's the whole building, thermal and air boundary. That's fair. Okay. Well, how about the out-of-grid photovoltaics?
We worked with Dogswood Solar on that. So because they had already started working on agrivoltaic garden in the community, we just used their information and their details to come up with our design.
Got about 4 minutes left if you guys have any more questions.
Sure, yeah. Do you guys think the garden increases the efficiency of the solar panels above them in any way?
Yes, it does.
Perfect. Yeah,
Yes.
because that's a good point. Like there was a case study that was done a couple of years ago. They clearly show that if you have something underneath the solar panels, keeping the temperatures in control, it's going to increase the efficiency. So I think inherently that's also an innovative feature, or not innovative, but a good feature to have. I did have one more question about the structural grid that you guys were maintaining. You said you have a smaller structural grid to do something. Could you elaborate on how that was accomplished, or what was the approach there?
The microgrid, is that what you're
Yeah.
asking? We decided to make the lighthouse a microgrid due to the fact that we need resilience in the community. And we also worked with the city of Columbia, Eric Warts, to come up with that idea as well. Yes.
Okay. Go for it. Go for it. If it's related, go for it.
Well, it's not really related. If yours is good.
Okay.
Yeah.
So actually, mine is actually to the building efficiency, and then talking about the unit mix, because this is for more or less students, correct? But you are doing a lot of one-bedroom units, and when we think about efficiency, maybe a studio would be a more efficient solution. And your ability, is there a reason why you backed off of having as many studios or things of that sort? Is there's something about that unit mix. By the way, the only comment that I'll slide in there is for your ADA units, you want them to be distributed amongst all of your unit types, not just the studios. But going back to the initial question, like, how did you really come up with the mix?
As an international student, I personally would like to live with other people. I get to interact with people, especially if I have friends. That's what made us decide these unit types, and that's why we have a little less studios than we do. Also, to have more accessible units, we decided to split the studios and accessible, considering the layout of our floor plan.
So the only thing I would challenge with that though is in your 31 bedrooms, you can probably split that one bedroom in half and almost double your quantity with the same density and reduce your price and your cost. Because if cost is your consideration, you do want to do that dollars per square foot and try to kind of mitigate and manage that. And so I'm with you in the idea of wanting to live together, but I think there are other solutions that you can find that are a little bit more efficient. For instance, could it be a studio without a kitchen? And then you have a shared kitchen. I think there are some things when, like, this works for a market rate unit, I think, or market rate product, and I think beautifully. But when I dial back into student housing, this is not necessarily the mix that really comes to mind. So I think that's just something to be considered.
Okay, thank you. Thank you so much.
So, yeah, I think it was electric resistance, domestic hot water. You had little heaters, maybe in every unit. I was kind of just wondering why that choice was made. Water heating is one of the biggest loads in multifamily. So, could you elaborate on that? The water heater selection, electric resistance specifically, it just it's not the most efficient option. So I'm wondering why you all went that way.
Okay. So we consulted with an MEP designer on that decision, and then the electric water heater ended up working the best for our scenario.
I think it's probably upfront costs are low. Like one thing we're doing in Seattle to push the envelope is we're moving to air to water heat pumps for domestic hot water that are centralized with large storage tanks because you go from 100% efficiency to 350% efficiency. So something to consider.
Okay, yeah, thank you.
All right, that's going to wrap up the Q&A. So let's give a big round of applause to University of Missouri. And we now have a 20-minute break from 10:40 to 11 a.m. Mountain Time. And then we will resume with Illinois Institute of Technology at 11.
I wasn't on mute. Thanks on there. Now there's an empty room. How do I get out of it? I don't know how to get out of it. What? There's nothing to record. How about signing out? Um,
We are going to resume in 4 minutes with the Illinois Institute of Technology.
Yeah. Just like the light.
Excellent. And then pointers. Yes. You guys will have access to the pointer.
This one right here.
That's okay, and that's.
Back and forth.
Good. And then, gosh.
All right, we are going to get started again here with Illinois Institute of Technology. You guys have 15 minutes followed by a 12-minute Q&A. I have the 2-minute warning sign. And whenever you guys are ready, I will start the timer.
All right, hello, we are Studio Zeb from IIT, and today we'll be introducing you to Liberty Arc. As you can see here, these will be the topics covered in our presentation today. The 6 of us will be representing Studio Zeb here in person, but these are the names of the team members that have worked on the project so far. So our site sits 6 miles west of downtown Chicago in the North Lawndale neighborhood. And this neighborhood is culturally and historically significant to the Chicago area. Our site sits on a historical boulevard system designed in 1909 by Daniel Burnham in order to beautify the city of Chicago and connect multiple communities to one central park system. Currently, this section of the boulevard system is underutilized, so we plan to breathe life back into the site with our design. You can also see the abandoned single-level story building that currently sits on the site there on the left. Our design caters to these 3 specific groups. The first one being local renters, who make up the majority of the community population, and they'll be looking for more affordable housing in the area. Local parents will be looking for community amenities for their children to use after school, and also specifically to those children because we want our design to be fun and educational and inspire them on the topics of environmental design. The community has faced some existing barriers that has prevented them from faster economic growth, and some of those being loss of community wealth due to spending not being done within the North Lawndale community, investment delays in current community projects, preventing them from faster economic growth, and disinvestment in community resources such as their local schools.
So fortunately, there are a handful of government initiatives that might benefit the North Lawndale neighborhood. On the federal level, the Justice 40 initiative from the U.S. Department of Energy might relocate some federal investment benefits to this area. And on the city level, there's been an ongoing campaign called Invest Southwest, started by Chicago's previous mayor, that highlights North Lawndale as one of 10 target neighborhoods for investment. Also, earlier this year, the current Chicago mayor committed $1.25 billion to neighborhood development, specifically for affordable multifamily housing. So we reached out to the residents of North Lawndale and tried to get a gauge of what sorts of programs they would like to see in their community. And we see that they feel a lack of spaces dedicated to community activities and events, with another popular answer being a library. So we felt the importance of including these programs as the main public aspects of our design. This is the portion of North Lawndale that we'll be focusing on. This piece is our site with its unique and challenging geometry. And this is how it fits into the Chicago Boulevard system and anchors it on this turning point. So on the northeast side of our site, where the street curves, our building's geometry gently curves to embrace the adjacent Independence Square and Fountain, which is existing on the site. And on the southwest side of our building, the massing is broken up and segmented to mirror the residential context. These scattered programs around the neighborhood of church, school, garden, and park, the current gathering places of the neighborhood, are what we hope to unify in this building for the community.
And in addition to reaching net zero, we created some design goals to care for the North Lawndale community. And by overlapping existing programming and the new programming, we endeavor to uplift the current community values. Here on the left side, or excuse me, the right side, you see the existing site. It is abandoned and undervalued. And on the right, you see Liberty Arc. It's the reimagining that the North Lawndale community deserves. It's not only inviting, but activates the site and the square adjacent to it. Here on the floor plan, you can see that the east facade is stepped back and it's a double-heighted arcade to allow for group drop-offs and meeting places along that street level right there. The blue is the residential portion and the entrance is on the north side to allow a little bit more separation and privacy. The yellow level in the middle is the flex community space, and these grand stairs lead up to this green library and working area up top. And then back down to the ground level, you see the community kitchen where local youth can learn cooking activities or local restaurants can try out new menus and overall just bond over food. And then the garage doors open up to that green area on the side to allow for outdoor activities. And then the building is actually mainly situated where the existing building is to allow for minimal disruption of the vegetation on the site. The top two floors are mainly residential. There are a variety of units and sizes to fit the typical working class family in the area. Here are the community events that we took from the North Lawndale current community calendar, as well as the interviews we conducted, and scheduled the programming to maximize the utilization in each of these spaces. Here are some vignettes that each space could cater to, such as senior daily activity, or excuse me, senior trips, farmers markets, and after-school activities. Here, this section highlights that the commercial portions are going to be mainly used during the day, and then here, the residentials are mainly populated in the night.
Chicago is an age rate climate 5A, which is a climate humid zone. We took this into consideration for the location of our PV, our massing, and our orientation. We have the wind rows, which shows the prevailing winds coming from the southwest and northeast of our building, which is where we located our fenestration to allow cross ventilation. On your right side, we have the sun diagram, which shows that the orientation of our building maximize the daylight and is still to help with the PV system. We did some buildings analysis to help us understand how the sunlight, daylight, radiation, and glare hours will affect our buildings. We then took these results to help us develop our envelope. To reduce glare hours, we designed this shading devices that are placed in the exterior of our envelope. These devices can be moved depending on the amount of daylight needed in each space. We also recessed the first and second level for the public area to define the entry and also reduce glare, since this facade is mostly made out of glass. We use glass because we wanted to blur the boundary between the interior and exterior. It was important for us to take in consideration the context and the development of our envelope. So we took inspiration from the surrounding architecture and color palette to then take this and translated them into our more modern and sustainable facade design.
We opted for a highly insulated envelope to minimize energy consumption. So both a commercial and residential section will have the same enclosure. Our wall strategy involved the use of large sheet panels as an exterior insulation to prevent thermal bridges. The large sheet panels are factory made, streamlining construction while ensuring an effective compactions against air infiltration. To meet ASHRAE recommendations, we decided to add a wood batt insulation layer to increase the thermal resistance. Each component of our enclosure is safeguarded by an interior vapor layer to prevent moisture to enter in the enclosure. One of our main goals was to create a building with a low embodied carbon. So we decided to use eco-friendly materials locally sourced in the United States. Our master structure is made of wood. So the wood is a carbon sink. It is renewable. And also after the building's life, it can be recycled. Also, our analysis showed that using the mass timber structure over the concrete structure resulted in a 50% reduction of the embodied carbon. And finally, our building received an A on a benchmark. There will be two ventilation systems, one for the commercial and one for residential section. It will be two DOAS system with an integrated ERV, energy recovery ventilator. The system will provide with a fresh outdoor air to the indoor spaces while recovering heat from the exhaust air. So it will reduce the energy consumption. Also, to meet ASHRAE standards, the ventilation rates comply with these standards and also will provide a good air quality to occupants and preserve their health. For the heating and cooling, we opted for an hybrid heat recovery VRF system. It consists of an air source heat pump that will be backed up with an electric resistance heater. This air source heat pump is connected to the bench boxes via refrigerant pipes, and these bench boxes are connected to the indoor fine cold unit with pipes of water. It minimizes the risk to occupant and to environment or by containing any potential leaks of in the indoor fine cold unit of water instead of refrigerants. Also, we reduce the total quantity of refrigerant in the building. This system advantages includes its capability to provide both heating and cooling, but also its ability to exchange heat between different spaces.
For our project, we also developed a smart water system to efficiently manage our water consumption. On the one hand, gray water will be collected, treated, and then reused in our toilet water system. On the other hand, rainwater will be collected to be reused for washing machines. This use of water allows us to drastically reuse our water consumption. We therefore estimate our reduction of water at around 17,000 cubic feet per year. In order to estimate our in order to achieve our annual energy neutrality, we set up a solar panel power plant on our roof. The solar panel chosen for our building are from the company SunPower, which is very present in the US. The solar panels will be orientated toward the southwest with a tilt angle of 22 degrees. This orientation allows maximum energy production in the late afternoon, which coincides with the peak energy consumption of our building. We estimate our energy production at around 30.7 kBTU per square foot. In order to estimate our energy consumption, we modeled our building on Grasshopper to finally obtain an energy analysis on OpenStudio. By using these tools, we were able to enter the different parameters and system chosen for our building. We estimate our energy consumption at around 27.5 kBTU per square foot, which gave us a balanced EUI of minus 3.3 kBTU per square foot per year. Unfortunately, the peak energy consumption and production won't always align. The peak energy consumption will appear early in the morning and late in the afternoon. To compensate that, we use battery to store our electricity, which help us enhance our autonomy for our building. When those batteries are full, the excess energy can be sold back to the electricity grid, and on the contrary, when our solar production is not enough to cover our needs, the electricity grid will supply our building. Furthermore, those batteries can be used can be recharged at night when the cost of electricity is lower. For the cost analysis, we used RS means. We did two estimations, the first one for the residential part and the second one for the commercial part. The total cost of our building is $8.4 million, which corresponds to $302 per square foot for the residential part and $351 per square foot for the commercial part.
And in conclusion, Liberty Arc is an anchor for the neighborhood and pumps life back into the boulevard. And it also creates space for the community to connect for a more sustainable future. We'd like to thank our industry partners and thank you for your attention. This concludes our presentation.
All right, we will move on to the 12-minute Q&A. Feel free to reference your slides as needed.
Thank you.
And I will start with Jason this time. We'll go right to left.
So just on the site selection and the project selection, I'm just wondering, while y'all decided to do a new construction project, there's a lot of, older buildings in Chicago that I'm sure could use an uplift. So just, could you explain more how you ended up with this project?
Thank you.
Sure. So we were introduced to this site by a former teammate of ours who had participated in some community events in North Lawndale. And he had collaborated with a church program pretty much a few blocks down from this site, and told us that he'd noticed the building on that site was an extension of the school that's directly southeast, but has been abandoned for quite some time and is underutilized. And to have a site like that on the Chicago Boulevard system, which is such a critical part of the city plan, we felt it would be important to propose a design for a site like that.
Okay, thanks.
Okay, so let's dig into that a little bit more. Because I think you're trying to solve a problem for the community. Let's kind of put the solar part to the side for a half a second. Because I think as architects and designers right now, we're trying to solve a problem, and you've created the narrative. Who is the community?
The residents and the locals in the neighborhood.
Who are they?
Do you mean like demographics?
Yeah, who are they?
Yeah, so it's mainly minorities, and has a problem right now, or they have a worry right now that any upscale development will cause more gentrification. So they want to remain true to their heritage. It was mostly a Polish neighborhood, and then during the industry, do you remember?
Yeah,
The industries left, like the Sears,
it was like a
industrial.
97% white neighborhood, and then in the late 60s, after the assassination of Martin Luther King Jr., there were a lot of riots that caused a lot of the population to flee. So it ended up being, within a few years, predominantly African American, and now with a large influx of Latino.
Okay, so I think you wrote that in your narrative. You did not say that today. And I think that's important because it's defining what solutions that you are trying to solve for. It also sets the market rate and the market center that you are trying to achieve, which then will inform what solutions that you need to provide for and how much efficiency that you need to present. It also then talks about another part of education that we would have a responsibility to potentially with our net zero or the economics and the efficiencies of our system. So I think we always have to contextualize, especially if that's the strength of what you're saying, we're building for our community and the community, you have to define the community, because that will give you a guiding light on what your solutions will become. I think it'll set some of your I think in your units, I think they could be a little bit more thought through or a little bit cared for, a little bit, whether we're talking about families or we're talking about I think I've heard you say market rate, but then I saw affordability. Those are really critical things that you have to answer. So I think while this was more observation, because I know you've created an object building that I think is beautiful. But I guess my question is, with that context, is there anything that you would adjust or rethink that would really inform what solutions that you may need to implement in your building?
Interesting. Thank you. I agree that we need to acknowledge the community for our solutions. I think when we did design our residential portions, we did try to match the current rate. I don't know, do y'all have anything that would change different?
We tried to design the different type of.
Could you speak into the microphone
yeah.
for our virtual
Thank you.
participants?
We tried to design the different type of units, considering that most of our community is going to be families. So we have one unit that has like 3 bedrooms and most of the units have 2 bedrooms, and try to minimize the 1-bedroom apartments.
Great. That's a great solution. Very great solution.
Did that answer your question? Okay, thank you, Reggie.
Perfect. I think you guys did a great job. Like you identified the problem very clearly, the target market. You actually let the occupants or the community develop the program, which is a great thing. So you had a clear idea of what people are looking for. So I definitely commend you on that. From an overall design perspective, I see that you have kept the focal point to be that fountain, and then you're using that as the focal point. But that's not the only thing that's available on the site, right? You have this whole boulevard. You're the corner or junction of that. I mean, design can be done 10 different ways. That's fine. I want to hear your thoughts on if you had done it slightly differently to include the whole boulevard in the design language, what would it look like?
Yes, absolutely. Thank you for that question. We did have some wonderful fun ideas at the beginning, but our wonderful engineers kept us grounded, and we kind of scaled back a bit to focus. I guess we initially had so many ideas that we wanted to kind of create this whole, or we really wanted to activate the whole thing, but I think when it came through the design process, we were like, okay, let's focus on this. Let's kind of more reiterate and focus more on this building. So that was in the design process. Do you have more?
Yeah. Last time we visited our site, we realized that the boulevard is actually being renovated, and then they're activating and creating walkways through these green spaces, because right now they're just like green areas that they're not walkable, but the city is trying to reactivate this area. So I think that our building in that location will be that perfect spot, because people can like then walk to our building to use or to get to the main events that we're going to provide in the community area.
Yeah.
So while the green spaces on the boulevard are not very utilized right now, they are open. But one thing we noticed was that the fountain currently has a gate around it, and there's no one really using it. It's just closed off to the community. So one thing that was part of our intention with this was, if the building can anchor that element of the boulevard enough, then the fountain could be opened back up and be joined with this element of the design so that it opens up that entire junction of the boulevard.
Can you point out the door, the gate you're talking about on the screen?
Oh,
It's like a fence around the fountain.
Yeah. Oh, I see.
there's a fence all around it.
Gotcha. Okay. Yeah. Well, thank you. Like, I
Yes.
know you must have thought about it, but we don't
Yes.
see it in the final design.
Yes, I
I just
understand.
wanted to understand what was like done.
Yes, thank you.
4 minutes left for Julie.
I'm really excited about this project. I think there are a lot of beautiful things that are happening here. We talked about community already, and I really appreciate the sensitivity with which you did the surveys and developed the program. But I would push you further than a general multi-purpose space. Even your renderings, you've kind of segmented the population. This is what happens when elderly people are in the space.
Okay.
This is what happens when this kind of thing is in the space, right? The
Mhm.
power, especially of these communities that you're talking about, is this intergenerational living.
Yes.
And so I would love to hear a little bit about how that, just leaning into your program, right? How that influenced the way you thought about the community spaces. Reggie already mentioned the unit types and the unit plans. And then I'd also ask you to delve in a little bit more on your thinking about the health and well-being aspects of the building and your life cycle analysis and the embodied carbon, and how you talked about trade-offs or synergies, especially when it comes to the interior finishes.
Thank you, Julie. I can speak more to the first one and then I'll pass it off. So one thing about our multi-generational population in this area, we did segment these, but I understand like we shouldn't have, but we wanted our units to be connected to these community spaces. So there could be more of like a community care for the youth. They really stress the youth or they stress they're passionate about uh developing the youth in their neighborhood with the adults. So I guess we just wanted them together, but also keep that separation for privacy. Does that answer your first question? Okay. And then for the life cycle analysis and then the wellness.
Sorry, it was also
No.
like part of the decision making was about scheduling different events in the building. So that might be why it seems so separate. We were imagining a rotating schedule based on what different people have going on in the day, for kids going to school, when they get out of school versus when other people might be available, and how that might affect the rotating program of the building.
Yeah, I guess my point is that when you have these kind of, when you're trying to catalyze a community and create those kind of community infrastructure systems, the programming is a critical part of the design and the enablement of that. And so by establishing programming that's just for one population at a time, you're not leveraging the intergenerational richness that happens when you mix it up.
I see. I guess I could add a little bit to that. So we have different activities, yes, but activities in the kitchen area and the community area could be happening at the same time. And we'll have that collaboration of this whole community all together. And we also have activities like the farmers market, because we realized that there are some like farmers around the area, and we wanted to give them a place for them to then come and sell their things. And that could be allocation for all the community to come together in those weekends, and also any other activity that they could or want to have. This could be the space to have those activities.
Great.
And then
All right.
to the interior.
That's going to conclude our 12 minutes. Sorry.
Thank you.
So let's give a round of applause.
Thank you again. Thank you. Yeah.
Thank you.
Thank you. And up next is going to be the University of Arizona.
As a tangent.
Oh, yeah. Okay. Okay. So you're gonna try to talk about it.
We're going to wait another minute or two just to stay on the schedule for University of Arizona.
The setup. Yeah, I think that's better. Yeah, rotate it. Does that work? Yeah. Give me the monitor.
Well, some of the others were like,
We have a professor who's notorious for breaking our models. Just, you know. They exist in every art.
makes you better, right?
You have a lot of practice in making models. How close do you have to be to the microphone? Well, if you feel better, check in the middle. So you can. get to the
Check?
microphone. I guess that's okay.
All right, I think we can go ahead and get started here. So whenever you guys begin, I will start the timer.
Good morning. We are the University of Arizona Multifamily Housing Team. Today, we are presenting Sihi Plaza, an ongoing collaborative project with the people of the Hopi Nation. We are a team of architecture students. I am Colleen Barbanti,
Janelle Hilton, Ashley Hume,
Chloe O'Hale.
And I'm Travis Reiner.
Hopi Nation is a remote landlocked area surrounded by Navajo Nation in the northeastern corner of Arizona. With a cold, dry climate, the summer months average a daily high of 93 degrees Fahrenheit, and the winter months average a daily low of 31 degrees Fahrenheit. The Native Peoples Design Coalition at the University of Arizona facilitated a partnership between our team and the Hopi Tribal Council. The council provided a flexible master plan for a new village, Tawa Ovi. Tawa Ovi roughly translates to Sun Village. The hope for the future village is that it will celebrate Hopi culture in a modern way and create opportunities for the Hopi people to flourish.
Hopi Nation uses a clan-based land system where land is passed from generation to generation within each clan. This new village will be built away from land currently owned by other clans with no political or sacred implications. The site currently has limited access to necessities such as grocery stores, public transportation, and healthcare options. The main grocery store, Basha's, is 1 hour away by car, while public transportation and healthcare options are at least a 5-hour walk. The nation as a whole is car dependent, making commercial spaces within walking distance a priority.
When we started this project in January, we traveled to Hopi Nation to speak with members of the tribe and get an understanding of their culture and their desires for this project. Key cultural practices and values that they wished for us to incorporate were an emphasis on food and the communal nature of cooking, agricultural traditions such as dry farming, water conservation, stewardship of the land, and unity. These cultural values became the backbone of our design process. Communal spaces, large open kitchens, terrace roofs, increased solar production, radiant flooring, and rainwater collection were all incorporated to promote sustainable and healthy living for generations to come.
The goal of this development is to bring more educational spaces, housing, and employment opportunities to encourage Hopi youth to return to the reservation if they've left or stay within the community. Of the registered tribal members, 70% of them have a family and about 50% have had experience with higher education.
Therefore, it's important to provide housing and commercial amenities that accommodates their educational, mental, and emotional needs.
Our mission is to create a FIAS Zero multifamily housing complex within a new solar-powered microgrid village. The project will respect Hopi cultural traditions and beliefs by promoting student engagement through community amenities and dwelling units that respond appropriately to the climate. The project goals address a culture of sustainability by using rainwater collection, a gray water system, and the use of prefab CLT. Exterior terrace spaces create room for traditional activities and provide a sense of visual connection to the land. Using native vegetation for the landscape, as well as replanting those on site, minimizes invasive flora and respects the land itself. Sihi Plaza is communally connected while also providing ample private space, assisting in healthy communal growth. Due to minimal access to utilities on the site, all three teams from the U of A have coordinated the development of a microgrid to assist in creating energy independence for the Hopi tribe.
Sihi Plaza houses students for an adjacent technical education campus. In addition, the plaza provides community of Tawa-Ovi amenities that are essential for the development of a master plan for Tawa-Ovi. In ASHRAE Climate Zone 5B, an emphasis is placed on access to sunlight. Therefore, Sihi Plaza will have maximized southern solar exposure for solar passive heat gain. To sustain life, we need sun and water. So a combination of gravel, runoff, collection skirts at the base of each building, as well as drainage concrete pavers and native plant bioswales help to aid in the growth of native flora. The Tawa-Ovi development guidelines have asked for trash compactor units, native plant spaces, and fire access roads. We have honored and continue to use the Tawa-Ovi development guidelines in the development of Sihi Plaza. Solar power is produced through rooftop solar, North Ramadas, Southeast Ramadas, as well as parking solar structures.
Hopi architecture traditionally incorporates plazas for cultural celebrations. The central pavers depicting Dawa, the sun god, grounds this plaza, making it an ideal space for ceremonies.
To assist the Hopi in stimulating the economy, creating new jobs, and reducing car dependency, the first floor is programmed with a variety of commercial and community service spaces. A post office and laundromat provide needed basic services. The combined market and cafe address the food desert condition on site while also providing a space for students and the surrounding community to enjoy meals with each other. The first floor commercial spaces are not only accessible to residents of Sihi Plaza, but to all Hopi.
The community kitchen provides a space for cooking classes, celebrations, and social events.
Some of the elders expressed a concern for maintaining health in the community. So a fitness center was incorporated in order for all Hopi on the reservation to maintain their physical well-being. Indoor treadmills, as well as an outdoor running path, provide two ways for Hopi people to express their deep love of running.
The bookstore works to amplify the voices of Hopi authors by selling books from writers in and around the community. The second and third floor have 12 dwelling units, which can house up to 27 residents. These units range from 1 to 4 bedrooms, with 75% of them being ADA accessible. The residents can access these units using an elevator or staircase located at each end of the building. They are connected by communal spaces featuring large open-plan kitchens and an in-unit laundry. The communal spaces allow students to engage in a more public area while maintaining privacy with their own bedrooms and bathrooms.
So all of these residential units have access to outdoor terraces, and this is to encourage students to not only engage with nature and its surroundings, but also each other.
The fourth floor spaces of the northern buildings include 2 greenhouses and wooden ramadas for drying agricultural goods. The colors utilized on each face of the greenhouse are meant to respect Hopi cultural traditions, where each cardinal direction is associated with a color.
All of the materials incorporated in the project were selected with cost, longevity, and environmental impact in mind. The glue lamp throughout the project is locally sourced. The lime-based paint and plaster sourced from California, have no VOCs, are hypoallergenic, mold resistant, and carbon sequestering. The butcher block countertops used in the kitchens are made from salvaged wood. The bathroom countertops are crafted from paper stone, which is manufactured from recycled paper and petroleum-free resin. The floors are finished with marmoleum, which is a 97% natural material and has a low carbon footprint.
The majority of these materials are also from relatively local companies along the west of the United States. This is in order to reduce the embodied carbon footprint. The structure of the building is composed of glulam southern pine columns and beams, and the floors are then structured with a cross-laminated timber panel system with radiant flooring overlaying. The floor is finished with a marmoleum, which is the sustainable alternative to vinyl. The wall is a well-insulated prefabricated panel system provided to us by Timber Age Systems, which will act as a continuous curtain wall attaching to the columns in order to prevent thermal bridging.
Tawa Ovi is located in ASHRAE Climate 5B. VS prescriptive values were utilized in order to create a baseline for an efficient envelope. This efficient envelope, developed with Timber Age Systems prefabricated panels, was chosen for a few reasons. The modular system helps reduce construction cost, time, and carbon impact. The Timber Age has also offered to teach tribal members how to fabricate and assemble these panels on site. The CLT used in the panels is beetle kill ponderosa pine, which would otherwise go to waste or contribute to wildfire risk. Alpin Windows is a Colorado-based company with experience in furnishing windows for passive house design. The proximity to site and quality of their windows were justification for choosing this company. The Hopi expressed a concern with dust infiltration, so tilt-turn windows were introduced in order to allow occupant control of ventilation while inhibiting dust that lowers indoor air quality. The south-facing windows have a solar heat gain coefficient of 0.5 in order to maximize winter solar gain, while the west-facing windows have a solar heat gain coefficient of 0.3 in order to minimize evening heat sun.
Radiant flooring is well suited for this climate as there are many days throughout the year which are very cold and very dry. The heat pump will heat up the water, which then feeds into a buffer tank, and this is where the water is held at a consistent temperature in order to assist with peak load hours throughout the day. The manifold is used in order to control where the water will go throughout the building, allowing different zones and rooms to control their temperature. The ventilation system uses Zender ERVs to ensure proper airflow into the building. The building meets FIA standards in regards to air changes per hour for the different types of spaces.
Hopi people practice water conservation in a variety of ways, including dry farming, where irrigation of crops relies on rain, and collecting gray water in order to water garden plants. Sihi Plaza incorporates both a gray water system to irrigate plants and a filtered rainwater catchment system that provides potable water. These choices help to greatly reduce the project's water footprint as well as honor cultural values.
The budget is currently $16.7 million, which is approximately $400 per square foot. Given the remote location of the site, labor and transportation costs were difficult to predict. However, this budget gives a clearer goal for Hopi people when it comes to funding. We do believe that fabrication of the CLT panels on site by Hopi tribal members will help to stimulate the economy while reducing the overall cost for this project and future projects in Tawaovi.
Sihi Plaza runs from an islanded DC microgrid, but it's not alone. Many of these microgrids are connected through a commercially available system called block energy. Power from the solar grid and individual microgrids are shared and optimized by a block central system, and then this redistributes in response to equitable need in the community. In the event of something like an outage, power will be diverted and focused on critical load systems to power perishable food storages, light utilities, as well as other essential resources. Block Home contains a block box sensors, battery storage, and a built-in DC to AC inverter. Rooftop solars produce DC power, which then powers block boxes, which then loop up together to connect to make a block loop. These powered block loops can then be distributed energy towards different batteries as well as EV chargers for electric vehicles. We have a projected energy use index of -88 and a home energy rating of -8. CE Plaza will use about 15% of the total 1 million kilowatt hours we expect to produce annually, that being 150,000 kilowatts, while adjacent microgrids in the community campus as well as attached housing will use about 35% of that electricity. The leftover 50%, about 500,000 kilowatt hours, will be used to power electric vehicles and can power about 100 electric vehicles over the course of a year.
The hope for Sihi Plaza, as well as Dawa Ovi, is to provide the Hopi with a precedent for future developments where they can exercise their sovereignty while preserving traditions. As we continue to develop the project within the coming weeks, we will meet again with Hopi tribal members to ensure we are focusing on their main goals, including water conservation, energy sovereignty, as well as expanding community growth. We will address our water conservation by further developing our rainwater collection and gray water systems. We will continue coordinating with Block Energy in the hopes of finalizing a plan for the budget and microgrid. And when we meet with the Hopi again, we want to ensure that the commercial program satisfies their desire for community growth and fulfills their need for economic stability.
We want to extend a special thank you to our advisors, David, Laura, Greg, and our Hopi liaison, Andrew, as well as our partnerships. We are incredibly grateful to have had the opportunity to work on this project with Hopi Nation. Thank you.
All right, thank you guys so much, and we'll get into our Q&A. So I'll start with Julie, on the left to right this time.
Congratulations. I think this is a really elegant project. You don't see so many that kind of seamlessly integrate the power and celebrate the indigenous culture and knowledge while not ignoring the building science, the engineering and all of that. And I think that for me, this was really synergized very, very well. And I'm actually struggling really hard to find a question to ask y'all that's going to push it to the next level and see if there's something else behind the thing that wasn't in the proposal. So here goes. Did you consider end of life and how, at the end of the useful viability of these structures, what happens to the buildings and all the stuff in them?
So part of the reason that we chose such natural materials is one, the modular panels would be able to be taken apart and reutilized for future housing if they don't want to use this building anymore. So those are completely reusable. When we talked with Timber H Systems, we got a lot of purview on how that might happen. The other thing too is the rest of the materials that we chose are, except for like our radiant system would be a bit more difficult to recycle, but a lot of the natural materials that we chose will actually be able to either be recycled or they aren't going to contribute to carbon waste because they can just be composted or some other format of waste, because like even our insulation it's cellulose. So we very much tried to minimize the amount of grave energy that we were producing.
Thank you.
I think the design is great. Like you guys have done a great job. You've kind of played with the idea of having a courtyard in the center, kind of creating the iconic design there. I'm assuming that's part of the design.
Yeah, so that's actually Dawa. He's
Yeah.
the sun god.
Uh-huh.
And when we coordinated with our liaisons, the Hopi said that was actually very appropriate to do. If you get a chance to see attached housing, they also did something similar because the village itself is named after Dawa.
Uh-huh.
And so, and in their culture, he represents hope. And this whole village, that premise is hope, because they're trying to revitalize the community and be able to, sorry, I'm gonna, they're trying to be able to bring their youth back and redevelop their community. So that was kind of our head nod to that.
Yeah, it's a great design. I really like it. The question I have is about the structure and the material. So we can see that you have played with the design with playing the design, you also create some negative spaces and irregular shapes, which is perfectly fine. It's part of the design process. But when you select the materials, let's say if we select mass timber or CLT panels, or a lot of other stuff, they come in standardized shapes. That means you might have a lot of wastage when you're trying to construct the building because there are small bits and pieces left around. How did you manage that process, or you thought about it?
Okay, so the building is actually built on a grid. It's a 10 by 10 grid. The way we designed it was for efficiency of use of materials. So the only spaces where it's a little awkward are those circular walls, which were a little head nod to cultural.
Special.
Yeah, they're yeah. So those walls are the like special economic condition. But we wanted to incorporate those in order to make that space as both as wide as possible, but also viewable from all of the communal spaces. So yeah, everything else is on that grid and it meets the timber age panel system. So we're gonna have very minimal waste. That's the only condition that we have that's like we let go a little bit.
Thank you. Can I ask one more question?
Oh, okay, because I'm
So
gonna
you have
to that.
so you have shown this to the community, right? Like, they have seen this.
They haven't seen this model or the final yet. The last time we met with them was like 2 weeks ago.
Okay.
And we had the general building form, but it wasn't finalized yet. We actually get to meet with them again in 2 weeks, I want to say, or next week. Oh gosh, yeah, it's next week. And then we have about like 8 tribal members coming down to see us and all 3 of our teams are presenting to them.
Yeah, I'm very curious to see how they react to it, but Reggie, it's your turn.
No, because I want to talk more about the panel because the panel's got me really, really intrigued. And I started off with the efficiency of like the arc and trying to get that off, make that happen. I'm like, all right, it's a panel. Sure. But there's a couple things about the components of the panel that I'm just wondering, is this panel supposed to come in with the stucco and all of the pieces already put together? Because I thought I heard you describe that they can figure out how to put it together. That's a lot of pieces.
Okay, so the timber age panel is just it's not the full envelope. So what we're talking about, and when we say the prefab panel, we're specifically talking about the CLT to the OSB. So that's your CLT panel, that's the BCI joists, the infill dense pack insulation, and the OSB sheathing. Everything else would be assembled on site.
Assembled on site.
Yeah.
And okay.
The BCI joists extend so that they interlock with each other. So that's how the roof interlocks and the panels interlock with each other.
So even more, okay, now I understand even more how you're achieving the look because you're going to site apply this stucco and you're going to get the monolithic look.
Yep.
That makes a lot of sense.
Exactly.
When you were investigating this wall, I know this is one system, but when we talk about the indigenous culture and the indigenous way of building and type, did you look at mass walls?
Oh yeah, we did. So one of the things that we looked at was we actually got to tour their villages and like their traditional homes. It was a very beautiful experience, but most of their homes are made from sandstone, which structurally is a little on the difficult side. And it's also very expensive for them at this current stage, because one of the things that actually CTE is addressing is the loss of masonry skill in the community. They used to be very adept at it, but that skill is kind of dying out. And so CTE is trying to like address that with their campus as well. However, when we were looking at a 4-story building, we didn't really think that that was the best route. We also really wanted to meet VIA's prescriptive standards. So a thermal mass wasn't going to meet quite the standards that we wanted. We wanted to be able to provide a modern home that would last a long time. And a lot of the villagers homes that we looked at were kind of falling apart. And we didn't want to run into that issue for them. We wanted to give them something that was going to last as long as possible to help build them a future.
great answer. Thank you.
4 minutes left for you, Jason.
Yeah, I mean, just echo everyone's comment. It's a super impressive design. So it's the desert. It's very dry, right? With mass timber construction, we see a lot of it may not be an issue out there, but there's a lot of you have all these prefabricated assemblies, and there's a lot that happens between prefabrication offsite and assembly on-site. They're subjected to all sorts of, it's like they're in a truck. They may be in the elements for a long time while the building comes together. The structure is exposed for a long time. I'm wondering, did you look at any of those constructability issues and, any risk involved and how you might address that?
Yeah. So one of the things that we talked about with Timber Age was they're actually looking to set up new facilities. So big collaboration with them. The initial stage would be phase 1, where the CTE campus would go up. And then the intent is that the CTE campus would house a space for them to prefabricate the panels there. And then phase 2 would be the development of our project and as well the attached housing project, so that they would be able to prefabricate those panels on site. That would create jobs for the Hopi and create a new trade skill, also increasing like their ability to create new homes on their own by providing this system. So yeah, that's kind of how we addressed that issue of getting to site. The other thing too is that Timber Age is located in Durango, so it's about a 200-mile drive. So it's not terrible, but it is, yeah, that is something that we definitely considered.
Very cool. And is the CLT, is that the interior finish?
Yeah, that is the interior finish. For all of the exterior walls, we left that raw because we wanted that biophilic nature connection.
Yeah, that's nice.
And then the interior walls are finished with a lime plaster and stucco.
Got it.
Sorry, not lime plaster and paint.
And is it the same with the floor assembly, that the underside of this CLT is exposed? Or is there
There is a soffit.
There is a soffit.
We
Okay.
soffitted that I think it's
There's
actually
a nice wall section.
Yeah.
there,
Okay. So if you look, the way we designed it was, well, I say we, Chloe did this. We soffitted the ceiling and dropped it with BCI joists so that we could increase the insulation for privacy, and also just improving insulation in our flooring.
Yeah, I wonder if you really need the insulation above the CLT. Maybe that's necessary for the radiant heat, but that just adds a lot of complexity. You could maybe put that radiant heat down on the CLT, and that roof looks a little under insulated. But I think it's like
I
a
did
cool, very cool
stress about it.
concept
It
to
is
do.
dense pack insulation cellulose. It's 71. It's just about.
Okay. Oh, you can explain that. I got it.
Because
Yeah, that
there's
makes
the
sense.
dense pack cellulose, and then the exterior of the decking for the terrace spaces, that is a 3-inch EPS insulation. So that adds us another bit of insulation. And then all of the rainwater gets collected from those raised floor plenums.
So I miss the dense pack cellulose. That's great. Say the rainwater gets collected from the. Can you run through that?
Yeah, so the rainwater is going to be collected from the roof. It's going to run all the way down. The terrace systems are it's a EPS insulation system, and then we have raised floor plenums so that any of the rain that hits those raised floor plenums directly will drain through the cracks of that floor plenum. And then the EPS is actually sloped. It's got a moisture barrier on top of it, and that'll drain down to the drainage spouts with our collection trough on the skirt of the building. And then
Alright,
that'll
I'm
go
gonna have
through
to
our
cut you
rainflow
off there.
system. I'm so sorry.
You finished your sentence. That's good. Okay.
Sounds great. Need to
That'll conclude our
Better on
12
the outside
minutes.
to capture
Oh, yeah,
All
it's
flat.
there.
All right, I'm gonna have to trying to stay to the 12 minutes. All right, so another round of
Nice
applause for
job.
University of Arizona. Thank you so much. And next up, we have University of Texas at Austin.
It has no notifications or bings and bugs. So I can just focus on, it's called a Remarkable. Yeah. I don't know, it was a gift. When people give me things, I try to make sure I use them, so
Yeah.
it's been forcing myself to try to figure out how to use it.
It's also very thoughtful gift.
Yeah, it is, it is.
It's a very thoughtful gift, like, that has some use. Sometimes people just use them. Oh, what do I do?
Maybe they're trying to tell me I'm too distracted, pay attention to one thing at a time. Did I come across as a really critical in the last, not this one, but this one?
Yeah.
Okay.
Yeah. He said that after last week, Arizona.
No.
Oh, just.
All right, we'll wait 1 more minute just to stay on the time. And there's a clicker there. And then I'll have the 2-minute warning sign. Okay.
Use this. With the.
Yeah.
No.
It's not working.
I don't know.
Right? Okay, sweet.
All right, whenever you guys are ready, I'll start the timer.
All right. Hello, thank you all for being here. Thank you, judges, for this opportunity. We are the Longhorn Solar Decathlon team, the UT Solar Horns from University of Texas at Austin. And we are happy to present Region Hall, which is medical student housing and also incorporates a community health clinic. So here is our team. We're an interdisciplinary team comprised of 10 students with backgrounds ranging from architecture, sustainable design, engineering, earth sciences, and liberal arts. And here is our faculty advisor, Dr. Michael Garrison. Here's our site. And first and foremost, our project wanted to address a real issue, which is student housing on campus. So the University of Texas has a student population of about 50,000 students, and yet is only able to house about 18% of the students. So for every 100 beds, only 18 students have beds. The University of Texas is actually building a brand new Dell Medical School facility,
which is going to be able to attract some of the brightest minds in medical from all over the world. So we want to give them a home. The University of Texas is split into two sides, which is West Campus, which is more busy and happening, and East Campus. Our site is located in East Campus, which is where more sports facilities are, and there's also some new graduate student housing. And the Dell Medical School is located right across 35. So it'll be a good site for walkability for students to also get to class. So when designing, we had to consider our climate zone. The University of Texas at Austin is located in IECC 2A climate zone. So this includes hot and humid summers, really hot summers actually, and then abnormal. We've actually been experiencing some abnormal freezing temperatures. So when considering materials, we had to find materials that would be durable in both climates. So a couple ways that we wanted to address these climates was with rainwater harvesting and courtyard design, and designing with microclimate. So we wanted to encompass our overall design into 3 design goals, which is affordability, sustainability, and compatibility. So we'll go over these design goals, and first I'll introduce Catherine, our lead design, who'll be talking about affordability.
Thank you, Michael. So for affordability, we decided to develop a replicable model that can serve as a reference for similar edge conditions for other university housing projects. We incorporated industrialized offset building process that not only enhances scalability, but also cuts material waste, boosts efficiency, has acquired higher quality envelope, speed of on-site assembly, and cuts labor costs. For cost, we actually worked with an industry partner, Oak Creek Homes from Fort Worth, Texas. And then we work with them to make a realistic cost estimate. And we ended up on a dollar per square foot of 173 compared to the industry standard of 300 in Austin, Texas. And by using modular construction, we were able to reduce our total cost by 70%, which let us leverage the incorporation of renewables and zero net energy infrastructure. And our total project cost was around $17 million. For our envelope, our installation values exceed building code requirements and comply with passive house standards and minimize heat transfer and enhances thermal performance. Our design features type 4 heavy timber construction, and it has a build smart edge tightness measure and responsive shading. We did a life cycle assessment with one-click LCA, and we were able to get a benchmark type B with 186 compared to the industry standard of 300. And for our carbon sequestering, we were able to have a result of 26,000 per year. And for our total operational carbon emissions for the year, it was around 4,000. And now I'll leave you with Sane, which is our engineer, to talk about sustainability. Thank you.
Okay. Thank you, Catherine. Hi, my name is Zane. And when considering sustainability, something that was really important to us, especially since we live in a 2A climate zone and we can go many days without any rainfall, was rainwater harvesting. Rainwater harvesting reduces our summer peak demands and also can help us incorporate evaporative cooling, which we'll talk about a bit later with our design for microclimates. So with our rainwater harvesting system, we have a basement with 15 units where we can collect rainwater, and these units can collect around 400,000 gallons of water annually, and that also includes surplus water. So compared to the Austin average, which is 88 days with using water without any rainfall, with our rainwater harvesting design, we were able to go 100 days with using water without any rainfall. So for our energy modeling, we did utilize OpenStudio. We modeled 1 out of the 3 buildings that we have and then extrapolated based off of that data. So in our OpenStudio modeling, we did in fact include the clinic. However, we couldn't include any clinic machinery because that is on the university's grid. So with our Open Studio results, we did end up getting a EUI of 21.1. And with our PV panels, we do end up being zero net energy. So for PVs, we utilize bifacial monocrystalline panels for high efficiency. And based off of our SunWatts calculations, we were able to achieve 455,000 kilowatts per hour per year for energy based off of our PV panels. And so compared to our power demand of our building, we utilize 353,000 kilowatts per hour per year. So that means with our PV panels, we do achieve zero net energy, and any excess energy that we gain because of our PV panels can be used for our clinic, or it can go back into the grid and be used for other university housing. So another integral part of our sustainability initiative for this project is design for microclimate. And so for microclimate, what we thought was really important was incorporating aspects of our design that we already have. So because of our modular design, we were able to design for microclimate because there is additional surface area for outdoor walkways, courtyards, and greenery. And due to our design for microclimate, we were able to save a lot of energy using design. So we were able to have shading from PV panels, cross ventilation, which also reduced the loads of the HVAC. We have 50% of green infrastructure and also evaporative cooling. So overall, our design for microclimate reduces the amount of climate control needed throughout our housing. It provides residents better connection to nature and the outdoors, and it also reduces our HVAC loads. So moving on to our HVAC system, we have a Minutair HVAC system with an ERV integration. It was really important for us to include duct layout because each unit where students will be living in will have its own HVAC system. So we need ductwork to be able to get that air from the outside and be able to supply it throughout our building. So with our ERV integration, we have air ventilation mode, which filters out pollutants, which increases indoor air quality. We have a recirculation mode, which maintains uniform humidity and temperature conditions. And most importantly, especially since each unit is going to have its own HVAC system, having temperature regulation can reduce our energy consumption, and the temperature regulation adjusts depending on both the occupants' needs and also the building needs. So overall, our HVAC system prioritize reduced energy consumption and also the occupants' well-being. So now moving on to Michael with compatibility.
So for our last design goal, we wanted to focus on compatibility, and not only compatibility with the university, students, and also the community. So first, the community. Here is our open facing community clinic. So we wanted to actually have a respectful height setback with the community and not have a design building that was kind of overpowering for the community. We actually work with people from the bordering Blackland neighborhood, which is also a marginalized community. And we have a direct quote from them saying, you know, that they didn't want another university building that turned their back on the neighborhood. So we wanted to have an open facing building with a courtyard that was able to be utilized by the community. We also wanted that respectful height setback, and then also to comply with university building codes. The University of Texas doesn't really like to build buildings less than 6 stories high, just because they want to have cost efficiency. So our Hein buildings are able to meet those building requirement codes. So also students will be living above the medical clinic and the Hein buildings. And there is a program that goes with the whole building design where first and second year students will be able to live on the first and second floors, and more senior students will be able to live on the top floors. We did this because in the medical school, we realized that students may be older, and some students may actually have families. So the rooms actually get smaller or get bigger at the top to comply with university students that actually may have families. And here is a site map that just shows the closer bordering with the Blackland community and how close we are actually. Like I said before, the Blackland community in Greater East Austin has actually been a marginalized community with the least access to healthcare in Texas. So our building design tries to actually foster better relations with the community. The community clinic is actually separated into two parts, which is in-person care and in-home care. So the residents of Blackland community are more senior residents who some might not have access to transportation to be able to get into the clinic. So the in-home care is ran by the nursing school, and they'll be able to kind of recognize community members who may need some in-home care. And then here's our community clinic, which is actually ran and operated by the students. Students will be able to work in the in-home clinic after 1 year of school. So the Dale Medical School is actually different. They like to focus on wellness. So the Dale Medical School wants to focus on more preventative measures, so we don't have to treat kind of intensive care. So with the in-home clinic and the community clinic, we'll be able to make sure that the community is more focused on wellness. And then for the program, I want to go back to this slide because it shows our layout with the units and actually the communal pod. So the senior most students will be able to kind of run study halls, and with the communal pod, people will be able to use a communal kitchen, which saves us kind of cost on appliances per unit. And so here is our overall design. We wanted to thank you. We also wanted to actually look at different ways that vertical mixed use could be used outside of just retail. So with the clinic, it gives us a vertical mixed use design that is actually more beneficial to community. Thank you all for being here. We are the UT Solar Horns, and thank you for your time.
All right, thank you so much, UT Austin. And I will get started with the 12-minute Q&A. As a reminder, any of you all can answer questions. You can use your slides as reference as well. I will start with Jason this time.
Okay, I'm gonna dive right into the HVAC system. So it looked like there was a heat pump combined with a heat recovery ventilator. So they're all in the one per unit. So I was wondering if you guys looked at the condenser unit layout, where those would be located. And is there one condenser unit per interior unit?
Yeah, so there is one condenser per unit for the HVAC system. Since it is in each individual room, there is like a small closet where the HVAC system will be located.
In terms of the exterior condenser unit where you reject heat to the outside, or?
Yes.
Yep. So it's a closet inside the unit, or?
Yeah, well, the unit itself
Uh-huh.
is in the closet, and because each room has its own HVAC system, each HVAC system will have its own condenser, if that makes any sense.
It does sort of, but the condensing unit, it has to go outside. It has to be
Yeah.
connected to the exterior so that
Yeah.
you can exchange the heat. So that's what I'm
Yeah,
wondering if the placement.
that is mainly solved by our air duct layout. So the closet, we have to use air ducts to be able to have access to the outside.
Mhm.
So that's why we have like air ducts within our system.
Okay, I still think you need to kind of fine tune that, and because there will be an exterior unit with each one of these, and you'll have to make sure you can run refrigerant to them, and so there's a little bit of fine tuning there. It sounds like to me.
Okay.
Actually,
Mm.
all our units
Mm.
have access to the exterior because we have an interior courtyard
Okay.
in one side, and then on the other side is the facade. So we have access.
So you
to-
could easily place them close to the units.
They
Yeah.
are in the units, yeah.
Well, where I think you're going is the unit that you have here on the screen, the Minotaur. There should, or maybe you can answer this. Is there two parts to this? Because there is the refrigerant that basically needs to run over the coils, that blows the air, the fan, that then either puts the cooling air or the heat. But that's usually exterior because of the exchange of the air. Is that a component of this, or is that's what we're trying to understand?
Yeah, the closet goes to the exterior. It's a place next to the exterior facade. So it has like an exit to the exterior for ventilation.
Okay.
Did you have any additional questions?
Well, no, I think, we'll leave it there.
Thank you.
Yeah.
I guess. So I heard you when you were talking about the students. I have kind of one clarifying question and then a second one about the unit mix and things about. So the first clarifying question is, all right, students, medical students, is that a graduate course or is that a undergraduate course? Like, is that first through second year postgraduate?
So this is for the Dell Medical Graduate Student Housing.
Okay.
And so this encompasses all years. So the way that the Dell Medical School works is that each grade level is actually a pod. So they all work together on one team. And so as the floors go up, they transform with that team as they go through. So the first floor has the most units to accompany that, and it's communal living so that you really have that shared mentality because it's so focused on teamwork within the school. And then as you move up, the number of units get smaller, but the rooms get bigger because medical students will be starting families. And so more of them will be moving out. So the entire design was to be built to go with how the medical school is run.
I think the only risk that you have there is because it's postgraduate, there are some people who graduate, take a pause, or need to do something else or find themselves, and then they already have their families, and then they're back in this first year with this group living, and it's almost kind of excludes them a little bit, even though I think it's well intended, because I think what can happen is the pods can be flexible.
Yeah.
And you can embrace that flexibility. So I really understand where, oh, there we go. Here comes my answer.
Like something we have in our not the slide appendix, but in the narrative was pictures of the plans and the and like renderings. And so the modules they have movable like heavy walls. And so even for lower floors, if you want to accommodate like a bigger, like you want to accommodate your family, you would just pull the wall back and rent both units. But if you want to accommodate more individual units, like for individual students, then you will pull the wall back. And so that's the kind of flexibility that we accommodate
Very
in
nice.
this.
And I used to be concerned about like, because here I am from Northeast, it's like double loaded corridor, here we go. But then I love how you can get the natural light or the daylighting from both sides. I love how you're playing to your region and
Yeah.
making that very specific. I think that works very
Yeah,
well.
we have a lot of like solar gain, and so that's why you have these can we show the picture of the operable window? Yeah, there's a lot of like yeah, and so these are adjusted with these wheels, kind of levers. And so depending on the day, the lighting condition can change and it could be more desirable or undesirable. And you would then operate the wheels to adjust that to your own comfort.
Very nice.
Also, it's our unit is 150 beds, so it won't be able to house the whole medical school. So it's an option for students, who want on-campus living.
Makes sense.
Thanks, Reggie. Great job, guys. Very good design. I'm sure the Dell Medical students would be happy to live here once it's constructed. And you were describing the problem very clearly in the beginning. Students need housing on campus. We don't have much. How do we design it? And provided a good solution for it. And the good thing I found about is the upfront cost analysis of how we are cutting the cost because of modular construction and then using it to offset the cost of PVs. I think that was a great move. Definitely commend you on that. Can we talk about how the other buildings operate on campus, the university campus? Did you think about connecting to them? You might have surplus at some point in time. Like, is there a thought process around that?
Yes, so actually on our site map, which is right here. Oh. So our site is located East Campus. There actually is a graduate student housing that has actually just been built by the University of Texas that kind of is adjacent to our site. So if we actually do have power, that they would be able to use that for generation, and also the medical clinic as well.
Thank you. Yeah.
In terms of like transportation or interaction, like community, like what do you mean? Can you clarify your question?
Absolutely, yeah. So two aspects. First, the design language around the campus.
I
That's
see.
fun. But the
Mhm.
other question was what you just answered. How does the solar grid or the PV system you have connect to the other buildings you have on campus? And not just the buildings you have highlighted, but like, do we have other buildings who have solar, or are you trying to combine them in certain ways? Because this could be a good option for them. So that was the question.
Yeah, I think Michael definitely answered the grid part that we have adjacent buildings. And then our site also faces our stadium and along with a giant garage. And so it's like our university is trying to expand into this neighborhood, which could be like argument on both sides, but the best that we could do is to enhance the design to fit better with the community. And then in terms of like design choices, our school uses a lot of like, I would say like Mediterranean kind of style of building, but in this one we chose more innovative and more I guess sustainable materials, kind of trying to get our university to be comfortable with the idea of different material choices. And then we have overhangs, and it's a big thing in any like UT buildings because of our climate conditions. So it is calling back to the design aspect in that area.
Yeah, and that was a good design move because I saw you had clear story windows right below the overhang, so you don't
Like
have any.
creative beams, kind
Exactly.
of-
So yeah, good job there, Julie.
This seems like a very nice place to live. I wish I was a medical resident. Your health narrative focused very specifically on metrics that were kind of one-liners. And we all know that doctors are the worst patients, and I assume the residents are even worse because they're underpaid and underslept and overworked and all that. Can you talk about your strategies to health that might be more comprehensive, integrative, holistic, preventative?
Okay, so we actually looked at the occupancy of the building, and we have with our HVAC unit, we actually looked at kind of indoor air quality for sure for medical students, because we don't want them getting sick as well. So we definitely chose an HVAC system that is actually gets rid of bioorganisms for more comfortability in the building. And then we also looked at acoustics as well for health, because we know that medical students sometimes have erratic sleep schedules. So we want to make sure that it's comfortable on an acoustic level to be able to sleep and be able to perform at optimal condition. So those were a couple health aspects that we looked at as well.
And then just to add one more thing, for the mental health side of things, the entire hall or the development is based around one central courtyard, and there is a lot of natural light for that mental health aspect. So there's a very much a strong connection to environment for them to go out and reconnect and kind of calm themselves. And then there are study rooms. If they need to take a break, as well as with the acoustics in their own bedrooms. We know that medical students might have really odd hours of sleeping. So we really try to take that into account when making sure that they could still sleep at a comfortable level and have like with the windows and everything, the right level of lighting to make sure that they're fully well rested. Because personally, or I think all of us wouldn't want sleep deprived doctors to be looking after us, especially because this clinic is so integral to the neighboring Blackland neighborhood, because they are very underrepresented when it comes to this medical source. So that's definitely an aspect that we took into consideration with our design.
Yeah, that's very much the type of answer I was looking for, because the built environment is a huge driver of preventative health, right? And you've got a captive audience here with residents, right? This is your opportunity to demonstrate to them that the architects, the designers, the landscape architects, the building scientists are their partners in this in terms of preventative medicine, which costs a lot less than the clinical intervention on the other end.
All right, that wraps up our 12-minute Q&A. So let's give another round of applause to UT Austin. So we'll now dismiss for lunch. You guys can head over to the cafeteria. Drink lots of water, please. You're at high elevation.
How much time did you really spend in the house taking care of students? I spent like 6
That moves by Suggs, and then a foul called on Jalen, who landed awkwardly, and he's holding his right shoulder. Jalen Suggs with the pressure, gets a deflection, going for the hustle play, absolutely, man awkwardly, coming underneath. He's Darius Darling. Yeah, right arm got pinned underneath him. Gonna stay in the game. Things have gotten physical. The Cavs have been right there to respond. Something they heard all about from last year's series. Mitchell, lost the handle. Nice touch by the Magic. 8 on the shot clock. And Suggs still in some pain trying to work through it. He's holding his right arm. Timeout called by Orlando with 4 minutes to go. And they have challenged. Move that one out of bounds off of.
Get one free Arby sandwich every week in April, online only. And see for yourself that Arby's sells more than roast beef. Spoiler alert, Arby's does. Arby's, we have the meat.
Did you know taking Zysol at night relieves allergies while you sleep? So you wake refreshed for a more productive day. In 24 hours, that does not fade. Be wise all, take Zysol at night.
We are going to resume in just a few minutes with the Cooper Union. So we will get ready here. You guys can come on up here.
Where's the clicker? What do you assign?
Oh, perfect. Wow, great. Yeah.
You should test it out a little bit. Yeah. Oh, you should.
And then it sounds like you guys will have some virtual.
Yeah.
For the Q&A.
Mhm. Maybe your timeouts.
All right, we'll wait another 2 minutes to stay on schedule. So just for your guys' awareness, I'll have this 2-minute warning sign. I'll hold up 2 minutes and then. I'll back up. So be on the lookout.
Yeah. Can I shift this back a little bit?
Yeah, the next one. Yeah, sure. All right, we'll go ahead and get started again with the Cooper Union for the Advancement of Science and Art. As a reminder, you guys have 15 minutes for your presentation. You can have 7 people presenting for the actual presentation. And then for the Q&A, you can have additional people. So whenever you guys are ready to start, I'll start the timer.
Hi, everyone. We are the Cooper Union Solar Decathlon team presenting our design for the Sure We Can in the multifamily division. Our team is made up of architects, civil, mechanical, electrical engineers, ranging from sophomores to seniors. Sure We Can is a recycling center, sustainability hub, and community space that serves as New York City's only nonprofit and homeless-friendly redemption center. The canners make an income by collecting, sorting, and redeeming beverage containers like soda cans and water bottles. This diverse community includes non-English speakers, unhoused people, those with disabilities, and the elderly, with most lacking access to the traditional benefits and protections of traditional employment. Our site visits to Sure We Can show that the lot is composed of a small building that is rented out, makeshift structures under which workers sort cans, shipping containers, and piles where bottles and cans are stored, a community garden, and a hangar for sorting, which features art projects made from recycled materials. Sure We Can purchased their lot last year for $3 million, and they're using a nonprofit finance fund loan and state grant, and they're looking to expand their facility. Our new 6-story modular construction will provide 22,000 square feet of transitional housing and support services while serving the canning process and storage of cans and bottles. We aim to integrate the canning and residential spaces to create a design that addresses Sure We Can's mission of supporting the local community and protecting the environment. Our site is located at 219 McKibben Street in Brooklyn, New York. Zoned for, the lot is 15,000 square feet, zoned for mixed residential and industrial use. There are 3 New York City Housing Authority or NYCHA housing complexes and several train lines located near the site. Sure We Can organizes community events with a nearby public school and local nonprofits, fostering a growing community. The solar altitude is much higher in the summer, and prevailing winds come from the south and northwest. The neighboring school also shades a large portion of the lot, and these details inform the orientation of our design to ensure that residents get natural light and ventilation, and canners are provided with a comfortable outdoor working environment. Sure We Can is in climate zone 4A, a mixed humid environment. Temperatures range from 15 to 100 degrees Fahrenheit, which will require the mechanical systems to meet significant heating and cooling loads. According to Sure We Can's 2023 survey of canners in New York City, a third of canners face physical or mental health issues, and the majority are more than 50 years old. Despite these challenges, this community continues to be vital to the cleanliness and sustainability of our city. In 2023 alone, only over 12 million containers were redeemed through Sure We Can, with canning overall reducing roadside litter by an estimated 70%. Canners often work without basic hygienic services and protective equipment, and with workdays ranging up to 12 hours a day, these workers need proper hygiene, living spaces, and community to rally around. Our project aims to combat the stigma surrounding canning and subsidized housing through thoughtful design. It has spaces for community events and provides social programs to assist unhoused canners in finding permanent housing and jobs. We maintain the center's goals of sustainability and the circularity of our design, and the materiality of the site emphasizes reuse and ease of deconstruction to minimize impact on the environment and existing canning activities. The design will streamline the canning process and efficiently integrate MEP systems with the architectural and structural features to reduce energy use and reach a net zero design.
The occupant's comfort and living experience and its surrounding site context are prioritized through our design choices. Our massing tucks into the shadow cast by the school across the street, ensuring that our design doesn't obstruct the views of neighboring buildings. Locating the canning operation on the public and communal space on the ground floor, we not only maintain the efficiency of the canning operation, but also insert public programming to cultivate a community that can also benefit and utilize the public showers, bathrooms, and canning office on the first floor of the short leg. The blue here shows the space for community events on the open ground floor with career center, residential management office, and laundry rooms on the second floor of the short leg. The 44 lifted modular residential units accessible through an elevator and 2 staircases lead into a 5-foot wide exterior covered circulation to access individual units. The L-shaped form of the building coupled with the widened exterior circulation creates a meaningful hierarchy of communal space between the residential units through visual and physical access. Ultimately, where the residents can bring life into the corridor space, further softening the boundary of private, semi-public, and public spaces.
The HVAC systems will be located on the roof of the short leg. In line with the modular design of the building, the equipment rooms are stacked in mechanical shafts that also function as structural cores. Air source VRF units exchange refrigerant with ductless mini splits to precisely condition the air in each zone. Heat recovery in the systems also reduces energy consumption and provides simultaneous heating and cooling to meet the varying thermal comfort profiles of the residents. The dedicated outdoor air system and DOAS will provide conditioned fresh air to each space. And given the wildfires from last year and decreasing trend in air quality, our DOAS system will use a MERV 13 filter as a measure of resiliency. The canning spaces are equipped with the exhaust fans that ventilate odors from the canning space, providing a better workspace and living space for the residents. The semi-enclosed space provides shading and protection from the sun and wind for the canner's comfort, while backup radiative heaters and outdoor fans will be used in extreme temperatures. The domestic hot water service will use an innovative wastewater energy transfer system that recovers energy from hot wastewater with a high COP heat pump. Our recirculation tank provides on-demand hot water for the comfort of the occupants and lifespan of the heating system. Non-potable rainwater will also be used for cleaning cans on the first floor.
A concrete podium will provide space for communal services, and our residents will lie on top of the podium, supported by concrete shear walls along the CLT core to withstand expected wind and storm loadings. One shear core will act as an elevator shaft connecting all floors to the podium. These act in tandem with the modules. The CLT walls provide extra lateral support, and more tension cables will be used to support the walkway and torsional loads. On top of the residential modules, a wood framed canopy is used to elevate and support the roof, while still giving accessibility to the mechanical equipment below. The residential and canning spaces will be completely electrified by the solar panels on both sides of the roof. Through iterative testing in Climate Studio and in a plug-in in Rhino, we found that the optimal placement of the PV panels were to lie flat on the 5-degree tilt of the canopy. This allows for self-cleaning of the panels and reduces shading from the panels themselves and other buildings nearby. This results in a 400,752 kBTU per year yield. The battery will store excess energy and we will sell back to the grid. In an emergency situation, we have an emergency pull-down switch, which will engage the battery, providing power to the residences for 7 days. And during heat waves, especially in New York City, the building will be able to disconnect from the grid and participate in incentives to reduce load from that grid. On the PV, the gutters along the PV collect 200,000 gallons per year. That filtered non-potable water will be used for the residential utilities, communal gardens, and to clean the cans and bottles.
Our modules are prefabricated with insulation and a vapor-resistive membrane before their installation on site. After placement of the modules, the building envelope will be installed. Factory-made modular components fit perfectly together and help with reducing the risk of gaps in thermal bridging between the facade and CLT panels. Our envelope uses double-pane windows and low-embodied carbon cellulose insulation to obtain an R50 roof and R32 walls that exceed ASHRAE standard. 20 by 10 CLT modules will come together to form the residential units. 2 modules will create a 1-bedroom unit and 3 modules will create a 2-bedroom unit. Each module will be constructed off-site via the Brooklyn Navy Yard and placed together with exterior walkway gratings and framing for easy modular placement and accessible plumbing integration. Each module is comprised of CLT panels, and both the floors and ceiling have acoustic insulation and in between each module and the interior walls for additional comfort. To begin the construction process, the site will be cleared of temporary structures and shallow concrete footings will be poured alongside the addition of covered communal space. Construction of the concrete podium will support the modules and provide additional space for the canning operation, allowing shurikens to remain operable during the construction period. Next, our CLT cores will be installed for structural stability and to streamline our modular installation for the residential units with layouts following optimal daylighting orientations. Our courtyard serves as an operable communal space, and the same construction process will follow for the short leg of the building. Installation of public amenities such as showers, bathrooms, and canning offices will be on the first floor of the podium. Residential offices, laundry, and the career center will be located on the second floor of the podium. Placement of the final 3 floors of the larger modular residential units will continue. Perforated screens are added to the outer shell of the building for additional privacy and glare reduction for the residential units. Then the mechanical systems will be installed. Finally, framing will be installed on top of the modules to support the solar canopy. Solar panels will then be added to the roof after roof installation.
Our site visits show that the main source of odor came from the cleaning and washing process of the collected containers. Our accessible canning space includes rainwater-fed cleaning stations and strong ventilation to mitigate this odor and ensure a comfortable environment for both canners and the residents. The enlarging of the existing communal space to coexist with the canning operation is dealt with at the scale of the furniture in the communal space, where the personal storage of the cans and bottles becomes a partitioning element that create flexible boundaries for various communal activities while maintaining visual and physical access to the main canning storage and operations. The designed wood furniture that houses the personal canning storage would form a dynamic and responsible relationship between the canners and public occupants. Since Shuriken works with a handful of container distributors, we thought of and included a designated storage for each of the distributors to streamline the offloading of the cans from the storage space to the trunks. With the proximity to the neighboring school, we also anticipate continued youth outreach programs and fundraising events for Shuriken.
The rotation of the module is paired with the perforated facade to create lighting control for the living units in the form of shading. This set a view oblique from the side of adjacent building, providing more privacy. Living units are connected through communal walkways for daylighting control and create triangular thresholds that function as semi-public outdoor space and form a collective living territory. 400 square foot single bedroom units along the long leg consists of 2 modules with 300 square foot of outdoor space. And 600 square foot 2-bedroom units at the short leg consists of 3 modules with 200 square foot of outdoor space. The bathroom and kitchen are placed to allow for easy installation and maintenance of the NMEP systems.
In our summer passive design for the modules, the perforated facade reduces heat gain and allows for natural cross ventilation. In the summer active design, we have mini split systems that provide cool air alongside a dehumidifier from the DOAS. In our winter passive design, the facade allows radiative heating into the pockets of air between the modules and the modules themselves. And for winter active, we have mini split systems that provide warm air alongside the dehumidified air from the DOAS. Natural light will illuminate interior spaces, reducing the energy consumption for artificial lighting. The light is oriented on a north-south axis, directing the modular layout to capture morning daylight for bedroom spaces with angled glazing on the east-facing facade. The angle of the east-facing window was iterated upon to reach an optimal balance of 50% daylighting spatial autonomy, with less than 10% of the space being at risk of glare. By relying on daylighting and efficient LED design, the lighting energy usage is reduced by 60%. Our energy efficient design has minimized our loads to reach a net zero energy building. Using energy modeling software in Climate Studio, we minimized heating, cooling, hot water, and lighting loads to estimate an annual use of 376,000 kBTU. Compared to the ASHRAE and typical inputs from the DOE, we are able to reduce our overall loads by 62%. This results in a source EUI of 51 kBTU per square foot before renewables, and after renewables, negative 3.4 kBTU per square foot.
4,300 square feet of solar panels with a 20% efficiency allows us to collect 400,750 kilobtu of renewable energy per year, making this building completely electrified. Since New York's fuel mix is roughly half reliant on fossil fuels, our building aids in New York's goal of being carbon neutral by 2050. Our project uses an integrated approach to material selection and module fabrication with an emphasis on reuse in both the construction process and in the circular ecosystem that Shuriken participates in. With locally sourced materials, intelligent use of recycled elements, and end-of-life salvageability, our project reaches beyond benchmarks for carbon impact.
Shuriken's existing shipping containers and corrugated metal front facade will be broken down to yield a total surface area 13,520 square feet of steel. The 5 40-foot shipping containers are used in the construction of the solar canopy, while five of the 20-foot shipping containers will be used in the creating bottle storage units that are animated to accommodate the fluctuations of bottles in and out of the site. The remaining shipping containers and front facade are used in the courtyard canopy, importantly maintaining Shuriken's characteristic murals into the most intimate part of the site.
RS means was used to estimate the cost of construction at $5.5 million at $276 per square foot. This includes the cost of construction, MEP, utilities, general requirements, allowances for overhead and profit, and contingency. Yearly financing consists of developer partnerships through low-income housing tax credits, along with rent, excess power, and the supportive housing loan program. The area has been increasingly gentrified, with rents increasing far beyond the capabilities of most residents. The majority of affordable housing in the area is distributed through lottery systems that require 150% area median income, or AMI, to even qualify. To combat this, 60% of the units will be transitional housing priced at 30% of Canada yearly income, while the other 40% will be community housing at 40% AMI. This project serves as a model for affordable housing that takes advantage of underutilized industrial sites while resisting the area's gentrification feedback loop. It serves the canners and the unhoused and aims to tackle the growing housing problem across New York City while reaching aggressive sustainability goals. We'd like to thank our advisors, design partners, Shuriken, and you, the jurors. We will now open for questions.
Thank you so much to the Cooper Union for the advancement of science and art, and we will move into the Q&A. I'll start with Julie.
Thank you. Excellent presentation. I'm a little confused because a lot of the questions that I had for y'all based on the project that you submitted seem to be different systems. Using things. But I thought I saw y'all say here that you were using heat systems for the individual units because the heat pump you didn't have space for it on the roof. You had to use all the space for solar. Am I confusing projects?
I think you might be using the projects we don't use at any PTEX. We have VRF systems on the roof and DOS for the conditioning of the air.
Okay, then let me go to my next one because I think you were also talking about an expanded metal screen, right? And I wonder why you chose that material as opposed to something with a lower embodied carbon footprint.
Well, the material that we use for the screen.
Could you speak into the mic, please?
The material that we decided to use for the screen is 100% recycled stainless steel. And this helps with the durability of the facade itself. And at the same time, still allows for the blocking of the solar heat gain and the allowance for natural cross ventilation.
So it's not a reused material or an industrial product or anything like that. It's just recycled content.
Yeah.
Okay, great. Go ahead.
Right. Great job, guys. Especially on the design side, I think it was very exciting, not just stacking containers on top of each other or modularity. You had a different way of stacking them, creating outdoor spaces. I think that was a great design choice. I think it's in Brooklyn, right? High density, very expensive. You're trying to create a space for people who might not be able to kind of experience that, right? So I think the impact is big, and you're trying to use those shipping containers and using the different components in different areas of the building. So I don't really have a direct question, but I'm just wondering, have you thought about what challenges would you face in taking those shipping containers off and actually placing them on different areas of the site? Because it's a very dense location. What are the safety concerns? Something like that. Does that make sense, the question?
Yeah, as Larry mentioned, it really is a model for thinking about affordable housing on these industrial sites. And so Sure Can also is planning to expand and have a satellite redemption center as well. And so we were thinking maybe that this modular construction could be actually like scaled up and be produced for not only Sure Can satellite site, but also for broader other redemption centers or even other industrial sites in that neighborhood.
If I can add, our construction process kind of splits up our development. So we allow for heavy machinery and, construction, the whole construction process, which also kind of allocates that space for the breakdown during the site clearing area. So that we've kind of allocated space for that as we move on.
So everything is on the site, the 15,000 square feet site. You just have spaces allocated. This is what's happening there.
Yes.
More of a construction management process, I guess.
Yeah.
Right. Thank you.
So my question is in the courtyard face in the corridor and the choice and selection of doing the open stair in New York, where you have all four seasons, inclement weather, rain, all of the above. What was the decision making for that?
With the good question, with the open staircase, we needed two forms of egress for any building in New York, and we really wanted to keep the porosity of the building so that there's no visual obstructions, vertical obstructions. And so with keeping the staircases as like porous elements that you can see past them, we thought that could sort of take down the intimidating factor of a 6-story building being constructed on the site.
Let me clarify my question, because it's not just the staircases.
Yeah.
It's also your interior corridors. They're open corridors. So if somebody's trying to walk to and from their apartment, they're out in the elements. And I just wonder if that takes away from the dignity of the space that you're trying to create, knowing where you are located.
Yeah, I mean, we were really trying to focus on sort of the visual connection and the visual connection between the residents and also the courtyard space, so that there is a sense of community and that there's not some like voyeurism where you can like see one way and you can't see the other way. We really wanted this to be sort of very a collective space, both like physically and visually. In terms of the actual it being like an exterior covered circulation, we weren't necessarily too concerned with that because I mean, we're just thinking of this like as an extension of the street that's like rising up, and then it's not necessarily like a typical apartment building in New York, but rather following more of a row house typology where you're actually entering the front of the building when you're walking. So it's sort of an extension of the street, and then you're entering the building as.
Yeah. And because I believe like the Sure Can is a really tight community, and we really want to like activate the communal walkways to be like part of the part of the collective spaces that within this community.
Can I jump in,
Yeah,
Reggie?
sure.
I really appreciate that. I think it's important as a part of the enlivening and activating the space. But you mentioned earlier too that the majority of the canners are 50 plus. And so, in snow and wind and rain, how are people, what's the safety condition there? I mean, yes, there's safety because you can see people and there are eyes on the street, even elevated. But because these areas are elevated, the conditions are a little rougher than they are at the street level, protected by the other buildings.
Yeah, I understand where the savings can be perceived, but if you need visual connectivity, you can always add, and even if you wanted to have, let's say, more efficient glazing systems or something to enclose it, I think that's just for the safety. The other thing I just wonder about is does it feed into a stigma? Does it make it feel like it's a motel and make it feel like it's wide open? I think there's like a double-edged sword when you think about when you can see everyone going in and out of their apartment. There is a safety concern two ways, because now you can be seen at all moments rather than being protected. So I just wonder about that. But then the other question I have is, did you think of this also as, I know you said transitional housing at some point for a home, and things of that sort. You decided to do apartments. Was there any thought to do make it more of a shelter? Was that ever in line or in alignment with your thoughts?
Sorry, could you clarify? What you mean by
So
shelter?
like a shelter, like a homeless shelter,
Yeah.
where it is basically a daily occurrence where people are coming in and out on a daily basis, because that may be something that could be more open potentially. I don't know. I'm just wondering if there was something of a thought, because then you're getting more occupants in and out as well. And I just don't know. I'm just rolling questions out because I forgot to lead with what I really, this is, I think is a very thoughtful project and very thoughtful process all the way around, how you've woven in the community, utilizing their old structure to create some of the canopies and also things of that sort. I think it's very thoughtful. I'm just thinking a little bit deeper into that social part of it. Go ahead, Jason.
Sorry, really quick. After talking to Sherry Can's director and also the people there, we really noticed that housing was something that they wanted, and so that was sort of like the pathway.
No worries.
Just as a small side note, I don't think the rules allow for us to do shelter type housing.
Okay.
But also speaking with Sure We Can, we saw that they kind of, it's not sort of meant to be like a blanket solution to, let's say, homelessness in general. It was more as kind of a sort of uplifting system where they could have the cares that they're so intermingled with and kind of give them spaces where they do have dignity, where they do have their own spaces to themselves, right? And then we also kind of mix that with social services where they can find other permanent housing and other sort of job support, like language, English services and other things like that, like job trainings. So our goal is kind of not to, shelter all of the homeless.
Oh,
that-
of course.
that
That's not gonna happen in New York.
accesses, yeah.
That's not gonna happen in New York. So
We're just,
I'm with
yeah.
you.
Got about 3 minutes.
Okay, so my question is coming from the perspective of having worked on a modular project, really two, where we ended up tearing a lot of the interior finishes out because they got wet during construction. So construction sequence has to be kind of very thoughtful and intentional. And I'm wondering, as these units get stacked and it looks like the HVAC is on the ceiling of the modular unit, like, and the structure is going up, also simultaneously. Have you worked through any of the challenges just sequence wise of keeping things dried in and, until those units are encapsulated and protected from the weather?
Yeah. So for that process, we thought of how we should construct our module. So basically we thought of doing a assembly line, basically in a warehouse in Brooklyn Navy Yard. And so the assembly line process will construct the modules, starting with the walls coming together, different interior finishes.
Okay.
And then on the outside, we decided to put our insulation and a vapor membrane on the outside prior to the placement on site, so that everything inside could basically stay dry. And then as each module is getting constructed, we would place the MEP systems for each module. And yeah.
Yeah, so that makes sense. And that's, it sounds like you have thought it through, but you get the horizontal ceiling, like, gotta just because we've thrown out so many finishes on modular construction. It's challenging. It's not typical. So it has to be very deliberate and intentional. So that's why I bring that up.
Yeah.
And I thought the heat recovery was really interesting I don't know if you got to in the presentation from the subway system and like the water down there. I have worked on a sewer heat recovery system. And it's also really challenging, but has the potential to be very energy efficient. So maybe you could elaborate for a minute.
Yeah, I can. We started talking with the MTA, with the Metropolitan Transport Authority, with a train company in New York, and at the end they were like, "Sorry, we can't share with the information of like the mechanical drawings and documents at this time." So we couldn't move on forward, but we were able to perform some rough energy calculations, like based on how much rainwater is collected during the summer, because that's when the rainwater will have higher temperature. This rainwater will be collected into pump rooms as stormwater, and then we can use like a heat pump or heat exchangers to gather to collect the energy in that hot water. And using some like very, very rough estimates, we were able to predict with the cost of construction of like installation of piping through the street and the amount of energy that we can recover from the hot water. There's like an estimate of a payback period of around 2 years. So I think, like you said, it's a very, it's an area where we can regain a lot of energy.
Yeah, got it. Okay. I think your infrastructure costs may be low on that because that piping and everything is quite involved.
Yeah,
But
it's
it's a
very
cool idea. And I'm working on a project with sewer heat recovery. We're actually taking water out of the sewer and using it for our heat pump system for building conditioning. So it's cool. It's innovative.
I know we're
All right.
close to on time.
I think we're at the end of our time.
Should we
Sorry, the
acknowledge
screen
the
just-
people who are on virtual though, very quickly? Because I want to make sure
We
that
are at time, so I don't want to give any advantage one way or the other. If there was one thing you wanted to show since the screen disappeared, I'll give you like 20 seconds. Just because. Okay.
or how about
Okay.
their faces? Let's
There are faces, but first, again, we just have some appendices to show sort of some plans that we would have cycled through. Just some sectional drawings, and also regarding resiliency, we actually are far from a flood zone, so we didn't have to worry as much about that. So we kind of focused our work on other areas. But we'll go back to the faces.
All right, we'll end there. Thank you so much. Can we give a round of applause?
I know.
Yeah,
it's
and for
worse.
repeat afterwards.
All right, next up in here is going to be Northeastern University.
Thank you.